Voila, I hope everything is hidden and that you can see the presentation. Yes, well, thank you very much for inviting me and giving me the opportunity to open this symposium. Frankly, I would have preferred to be in Grenoble. I miss the canteen very much. But on the other hand, there are advantages in this situation. At 11, I will have the closing talk at a conference in Osaka. So this would have been hardly feasible in physical presence, but like here, it would be enough to ask Zoom to beam me up in Japan, and this would be done. As you all know, actinides are an important test bed for the development of our understanding of quantum matters, of condensed matter physics in general. They allow investigating new classes of material behavior. They are at the brink of magnetic instability in a region where quantum fluctuations of magnetic and electronic degrees of freedoms are strongly coupled. So relativistic effects are important. Orbital degrees of freedoms are not quenched. There are several electronic correlations with similar amplitude competing. Electronic correlation are strong. Hybridization between the F electrons and the conduction electrons is also important, leading often to a dual localized itinerant character of the 5F electrons that form narrow bands. Also, actinides have played an important role in exploring a region which is not yet fully known, which is the intermediate between the nanometer and the millimeter scale, where emergent properties are not yet fully understood. On the other hand, X-ray synchrotron radiation techniques, being elements and shell specific, provide a battery of powerful tools for studying the properties of actinides. This is because they allow us to probe the spatial and temporal fluctuations of the structural and the electronic degrees of freedoms, and to characterize elementary excitations with high sensitivity and resolution. Also, they allow observing order parameters that are not visible with other techniques. The question to answer are, in principle, quite fundamental, quite basic. Actinides are also on the verge of lattice instabilities and shows open-packed crystallographic structure and the rich polymorphism. To study these aspects, high resolution and high pressure X-ray diffraction studies have been, of course, very important. In particular, high pressure X-ray diffraction. Here, I try to put the pen like this. You can see the equation of states for 3 elements, alpha uranium, curium, and americium. In some cases, one observes some volume collapses, indicating a partial delocalization of the 5F electrons, and then the partial participation to metallic bonding. These kind of experiments have been important for the development of first principle calculation scheme. So for developing approximation of the density functional theory with the capacity of predicting the behavior of actinides. In the past 20 years, this has evolved from say something comparable to the predicting capability of social sciences to almost a material by design level. Of course, there are properties that are still a challenge to understand. For instance, the volume dependence of the superconducting critical temperature in americium that you show here across the different phases is certainly still far away from the modeling capacity. Another simple question to answer is which valence state do actinides adopt? And which is the approximation that better describes the building up of their atomic states, and also how large are the spin and the orbital components of their magnetic moment, how they combine to give the total magnetic moment. To answer these questions, X-ray absorption spectroscopy, XAPS, XANES, XMCD have been very instrumental. In particular, X-ray magnetic circular dichroism has proven to be very interesting. The edge of choice for actinides are the M4 and M5. These techniques probes the difference in the density of empty spin up and spin down 5F states. The unbalance can be produced either spontaneously in presence of ferromagnetic order, or can be induced by applying a magnetic field to the sample. And then the absorption are measured for across the spin orbit split edges for photons with opposite helicity. The power of the technique is due to the simplicity of the sum rules that correlate the linear combination of the dichroic signal at M5 and M4 edges with the physical quantities, the angular momentum component along the magnetic field, the component of an effective spin moment, which is the sum of the spin and of an operator called magnetic dipole. Experiments have been done on a number of compounds with different symmetries, different characteristics, different physical behavior. For instance, here you see the signal obtained for a actinide iron 2 compounds from uranium to americium compared with the signal measured for elemental curium. A visual inspection of this spectra immediately tell basic properties of the atoms. For instance, you see here that for the light actinides, the peaks have the same sign. For curium, instead, they have opposite sign. This immediately tells us that while spin and orbital moment are parallel up to americium, they become parallel for curium. Also, the area of the peaks at M5 and M4 in curium have not the same amplitude, then the sum is not zero, and it means that despite being the analog of gadolinium, curium is not a pure S ion, but carries a angular momentum which is different from zero. The advantage of the techniques in determining orbital and spin moment compared to polarized neutron diffraction is essentially on the size of the sample needed, which is up to a factor 10,000 smaller for XMCD than for polarized neutron diffraction. Also, you don't need single crystals to carry out these measurements. And if you are studying superconducting compound, you can take advantage from the fact that XMCD is not sensitive to diamagnetism, but will explore only the behavior of the 5F of the interrogated shell. A problem is the determination of this operator, this magnetic dipole. Well, for several compounds, this quantity is known from independent measurements, for instance, neutron diffraction, or in the case of neptunium compounds from Mossbauer spectroscopy. Studying, trying to build a systematic in this case, lead to the discovery that the ratio between TZ and SZ is essentially well described by intermediate coupling approximation models. Not JJ, not Russell-Saunders, but intermediate coupling. Then when you are not able to you cannot use independent information to estimate TZ from experiment, you can calculate this in intermediate coupling approximation and then determine the other two quantities. Recently, just a few days ago, there was a paper in Nature reporting trace level X-ray absorption spectroscopy on a complex of Einsteinium. So this is element 99, half-life of about 280 years. The experiment was performed at Stanford on a sample of 100 nanograms. Well, measurements at the L3H 77 Kelvin confirm that also in the case of Einsteinium, intermediate spin-orbit coupling scheme is working well. Open questions concern the electronic structure of actinides, and information on the detail of the splitting into multiplet, for instance, is obtained by resonant and non-resonant inelastic X-ray scattering. Kinematical parameters are defined as in neutron scattering as the difference between incident and scattering momentum and as incident and final energy of the phonons. Non-resonant inelastic X-ray scattering occurs if the incident photons have an energy far away from an absorption edge. In this case, the process is simply the promotion of an electron into an empty state and the creation of a core hole with the emission of a photon of different energy. The cross-section can be calculated using the Born approximation, then using the Fermi golden rule. And if you expand the interaction operator into spherical multiples, the order of the multiples allowed are limited by triangle conditions and parity rules. So if you are addressing a transition from a D to an F state, only kappa value of 1, 3, and 5 are allowed. Dipole, octupole, and triaconta dipole. These different components of the amplitude are weighted by radial matrix elements that have a strong dependence from the momentum transfer. Therefore, at small values of Q, you will probe essentially the contribution due to dipole transition. The spectra will be equivalent to those measured in absorption spectroscopy. Whereas if you go to higher and higher Q values, the dipolar component contribution will fade out, whereas the octupolar and the triaconta dipolar contribution will increase. Then the final state addressed will have a larger momentum and less energy. This means, as you can see here in spectra obtained from uranium dioxide, that going below away from the Fano resonance, the spectra becomes a much better defined. Structure of the multiplet appears, and this can be modeled by many electron atomic spectra calculation or also by first principle band model. And then the technique can give you information on the system. The talk of Andrea will, I think, give further details on this phenomenon. There will also be a talk by Martin Sanderman that will show how also in cubic symmetry, the presence of multipolar term introduce a directional dependence on the Nix signal. And this directional dependence, that you see here in UO2, but Martin will show in detail, give access also to the crystal field potential. These experiments are done with photons with the incident energy of the order of say 10 kilo electron volt, which means that is a bulk probe, and it is possible to study encapsulated samples. Indeed, experiments have been performed also on transuranium samples, neptunium, plutonium, oxide, and sesquioxide, for instance, and the results will be shown in the contribution of Simo Watari to this symposium. If the photon's energy is tuned to an absorption edge, we enter in the regime of resonant inelastic X-ray scattering, of resonant emission scattering, depends which channel of decay you are measuring. For instance, at the L3H L alpha 1 emission line, which is in the region between 17 and 18 kilo electron volt, a 2p electrons will be promoted into an empty 6d states, and then the core in the 2p level will be filled by at the L alpha 1 emission by a 3d electron. And then you can measure core to core signal or valence to core. And the difference is that in the first case, the final state has a core all, in the second case, not. Well, experiments have been done at the N 4 and 5 age. In this case, the incident energy is of about 750 electron volt. You can achieve a resolution at I21, for instance, a diamond of 35 milli electron volt, which is enough for resolving the crystal field excitations in the 5F2 configuration, and to observe intermultiplet excitations. This is, for instance, the transition from the 3H4 to the 3F2 multiplet that are very difficult to observe with other technique. Again, the talk of Martin Sanderman will present the results obtained. At the N4H with 750 electron volt, the penetration is of the order of a few nanometers. Then this is certainly a surface technique. On the other hand, at the MH, the penetration is of the order of 200 nanometers. And then the technique starts to be essentially a probing the bulk properties of the system. These are, for instance, the signals obtained for a series of uranium compounds at the M4H, exploring the M beta emission line. So then is the all is filled by a 4F states. Transition at 3.3 kilo electron volt. As you see here, the green curve and the blue curve corresponding to uranium palladium 3 and uranium ruthenium 2 silicon 2 respectively are essentially superposed. Now, uranium palladium 3 is an intermetallic compound where it is well established that the electronic configuration is 5F2. Then this experiment suggests that also uranium ruthenium 2 silicon 2 has a 5F2 configuration. Of course, it could be the case that the surface layers are oxidized, but in this case, the spectra should be similar to the one of UO2, which is an insulator. And you see that there is a shift of about 1 electron volt between the two cases. So then the indication of these experiments are that allows to give a strong indication about the valence state of the compound. There was a unexplained results in this spectra. If this is the RIX maps, and if you highlight the region below the spectrum, you will see the appearance of a feature that was not expected. I think that in the talk of Sergei Butorin, the origin of this feature will be explained. RIX experiments or beta X-ray emission experiments have been performed also at the L3 edge. In this case, in the case of americium, for instance, the incident energy is of the order of 18 kilo electron volt. This then is a really penetrating probe. The experiment was performed in a diamond anvil cell to explore, to verify a prediction of the dynamical mean field theory concerning the appearance of intermediate valence state in americium-4. Which is an orthorhombic phase, whereas in the double hexagonal close-packed americium-1 phase, the electronic configuration is a non-magnetic 5f6. The mixture of the 5f7 state with a large moment was predicted, but in this case, you would expect an additional emission lines below the main peak. And as you see in the left and the right panel, where the RIX data are reported for the pressure corresponding to americium-1 and americium-4, this additional emission line is not seen. Then in this case, at least, dynamical mean field theory failed to describe the system. Until now, I've spoken only about atomic behavior, but X-ray techniques are very important also to understand the collective behavior in actinide systems. And an important question is the nature of the ground state. To answer this question, resonant X-ray diffraction has been very important because it allows us to reveal the nature of what is called hidden order in some, at least, actinide compounds, in particular in the oxides. In this case, the scattering is elastic. The photons are tuned to an absorption edge, promoting the electrons to an empty states. And then in presence of long-range order, the intensity of superlattice peaks are measured at resonant energy as a function of the polarization channel, mainly using linearly polarized photons with polarization parallel or perpendicular to the diffraction plane, and by measuring the modulation of the superlattice peaks as a function of the azimuthal angle, that is, while rotating the sample about the scattering vector, the Bragg peak vector. The relevant amplitudes, the important ages are again M4 and M5, because the transition is to an empty 5F states. At these ages, the dipole-dipole terms of the transition have essentially three terms: a trivial one, which is probing the charge, one which is probing magnetic dipoles, and another which is probing electric quadrupole. At the quadrupole energy, instead, other tensorial amplitudes appear that in principle allows one to study electromagnetic multiples of Eiger order. However, only indirectly, because in this case, the interrogated shell are 6G, 7S, 6D. If you want to observe directly at the quadrupole edge, the 5F state, then you have to go to the M23 and to the L23 edges. Some attempt has been made, but with unsuccessful results. Instead, important results have been obtained on the actinide. The important ingredient is the crystal field ground state, which in the case of uranium is a gamma-5 triplet. In the case of neptunium is a gamma-8 quartet. Now, the gamma-5 triplet support magnetic dipole and electric quadrupole degrees of freedoms. In the gamma 8 quartet, also octupoles, hexadecapole, triaconta dipole, and rank 7 magnetic dipole. Well, in the case of UO2, neutron diffraction revealed many years ago that the primary order parameter are magnetic dipoles. Resonant X-ray diffraction showed that electric quadrupoles order according to the same motif as secondary order parameter. On the other hand, in the case of neptunium dioxide, neutron diffraction and other techniques failed to identify the primary order parameter. Instead, by resonant X-ray diffraction experiments, essentially measuring superlattice reflections corresponding to some order, revealed by an analysis of the polarization channel here, sigma sigma channel and sigma pi, that is incident and final polarization perpendicular to the diffraction plane, or perpendicular and parallel in the case of the white points, and modulation of the intensity as a function of the azimuth angle, reveals that the secondary order parameter are electric quadrupoles of gamma 5 symmetry, forming what is called a triple K longitudinal order. The primary order parameter can be established by combining this observation and inelastic neutron scattering, and the result is that is a rank 5 magnetic multiple. The technique has been used also to try to explain, to observe the hidden order in uranium, ruthenium 2, silicon 2. In this case, a phase transition is observed at 17 Kelvin. The anomalies in the heat capacity, in the resistivity, in the magnetic susceptibility are very large and cannot be explained by the presence of an ordered magnetic moment along the z-axis shown by neutron diffraction, which is of only 0.03 Bohr magneton, too small to explain the change in entropy, for instance, at this transition. A number of theories have been proposed, proposing as order parameter electric multiples of different symmetry, or even in the framework of a delocalized model, Fermi surface reconstructions and dynamical symmetry breaking, or exotic phenomena like one including a double channel Kondo mechanism with a coupling operator, which is itself a spinor, and then leading to an order that is breaking simultaneously both single and double time reversal. This model was called a static order. Well, the results of X-ray diffraction shows the presence of superlattice reflections. For instance, here the azimuthal dependence of the 201 peak, but the azimuthal dependence of the intensity of this superlattice reflection and the polarization analysis are explained only by assuming a magnetic moment along the z-axis, as already shown by neutron diffraction. All model based on ordering of electric quadrupoles of the different allowed symmetries and different motifs provide a profile which is not compatible with experiments. Moreover, this astatic order model would imply the appearance of a component of the order and moment also in the AB plane. This can be checked, and you see that adding such a model component in the plane is increasing the width of the main peak in the azimuthal dependence, and is changing the intensity of the smaller peak. So an analysis of the data showed that if such a monument component is present, will be smaller than 3 millibor magneton, whereas the theory predict a moment as large as at least 0.1 Bohr magneton. Lattice dynamics and collective excitations are also an important information that you want to have to understand the behavior of the system. For instance, collective excitations will influence macroscopic properties. The transport properties of actinides are important for their application. In this case, is the high resolution inelastic X-ray scattering, which is the crucial technique. Here, experiments are performed with the energy resolution of the order of the milli-electron volt. And experiments, of course, have been done. For instance, the lattice dynamics of UO2 was extensively investigated by inelastic neutron scattering already in the mid-60s. These curves are the dispersion curves for UO2. In more recent years, the investigation have been extended to high temperature, to above 1000 Kelvin, essentially to study the broadening of the phonons. However, similar studies have not been possible for neptunium dioxide or for plutonium dioxide, essentially because of the size of the available samples. The picture here shows the crystal that we used for almost all of our inelastic neutron scattering studies, whereas this dot here, this is the largest single crystals available for neptunium dioxide. Those for plutonium dioxide are much smaller. Neptunium dioxide has the mass of a milligram. The crystals for plutonium dioxide have a mass of 1 microgram. Still, this is enough for inelastic X-ray scattering. And these are the dispersion curves that we measured on ID28 for neptunium dioxide, and were good enough to benchmark direct method calculations of the phonon frequencies and half-life calculations that then have been used to model the phonon contribution to several thermodynamic quantities of practical importance: thermal expansion, specific heat, thermal conductivity. Well, also in the case of uranium dioxide, as you will see in a talk by Luigi Paolasini, inelastic X-ray scattering can be very interesting because they provide information complementary to what you can observe with neutrons. For instance, in the case of uranium dioxide, what you would expect for what you would expect is a continuous phonon dispersion and only 2 magnetic branches, even in presence of anisotropic superexchange interaction, but with just 1 optical spin wave branch and 1 acoustic. That should be the 2 branches degenerate at the zone center, and they have the same energy at the zone center and at the zone boundary. Instead, neutron experiment shows a much more complicated pattern. This is because of the strong magneto-vibrational interaction and electric quadrupole vibrational interaction. These interactions and the presence of strong contribution to the superexchange field of multipolar origin, so in particular quadrupolar superexchange coupling, a number, at least 2 or 3 strong avoided crossing points are present with the formation of mixed spin phonon modes, mixed spin quadrupolar modes, and mixed quadrupolar phonon modes. For instance, here, this is the anti-crossing between a transversal acoustic phonon and the spin and the acoustic spin wave branch. What happens at the anti-crossing positions is that the mode is a linear combination of magnetic and phonon modes. Well, neutron experiments are performed at low temperature with small momentum transfer, and in this condition, it is difficult to observe the phonon contribution. And then essentially, this is a map of the magnetic part of the mixed excitations. On the other hand, with inelastic X-ray scattering, you measure directly only the phonon part, and then you can have access to the complementary, to the mixing information in this scenario. So Luigi talk will show the results obtained in UO2. So I'm the end of the talk. I've presented the results of studies that we have performed during the past 20 years, 25 years. The number of collaborators is too long for a 40 minutes talk. Already the number of the institutions that have been involved is very large. There is only a, say, physical constant in all this study, and this was the presence of Jerry Lander, the chairman of this talk. So that's all. Thank you for your attention.
Okay, I think this thing should work now. Does it work? Yes. Thank you, Roberto, very much. Now then, we have only got one question, Roberto. First of all, you're right on time, so I congratulate you for that. And the one question that I see in the question and answer thing is actually from Francesco Setti. I don't know if Francesco's still here, but anyhow, if you are, welcome and hello. And Francesco's question, it's more like a comment, really.
How can we be sure that the battery is not aging?
That's right. That's right. How can we show the battery is not aging?
Well,
yeah.
Actually, it would be aging if the technique would not evolve constantly. Because once you have answered the most important question, it's clear that building a systematic would not be useful. But for instance, I've shown the example of this paper published in Nature last Friday. This was done on a sample of 100 nanogram at a synchrotron, which is certainly not comparable with the capabilities that are now available at ESRF. But it's already a demonstration that the possibility are now open to extend the investigation to samples that you cannot study on the milligram scale, as we did for uranium, neptunium, or plutonium. Then I think that this is the answer, that the evolution of the technique will first allow studying details that are not accessible, that have not been accessible until now. And in the case of actinide, that are opening the possibility of studying a sample with smaller and smaller dimension and then activity. For instance, several years ago, we made an attempt of doing tomography on fuel. Of course, the test was done on non-irradiated fuel, but just a cavity introduced artificially. Well, the experiments were not affordable, were not successful because of the size of the sample that we had to study. Now, it would be possible to study samples prepared by focused ion beam technique. And if you go to a sample of the order of, say, 1 micron scale, even a really irradiated sample should be accessible. And I think that with the new lattice, this would be accessible.
Okay, okay. Now, Francesco's made another comment here, which you may see, Roberto.
It's very, very small. And, you know, I need a microscope.
We need to consider new
it's not
access
aging, but
modes.
experiments are becoming more and more demanding. Do we need to consider new access mode?
Well, I think when you talked about the Einsteinium, you said that had a half-life of 280 years, but I think it's 280 days, isn't it?
280 days, of course. Yeah, it's less than 1 year.
So under those conditions, Francesco's remarks are very pertinent, because of course, if you have 280 days, then you have to have your sample and you have to do the experiment quite quickly. So you have to plan that in advance. But I think that can be probably arranged at the ESRF. I don't know if it needs some new access, but yeah. What do you think about
new access? I was fond of the possibility that was allowed years ago of the long-term proposal. For actinides, this was very useful. You remember we had several of them running for extended periods up to a couple of years. And these were useful for us to build the environment, the sample environment that we needed to check for the absence of contamination and so on, but also to test the techniques on these systems. This would be important. For instance, in the case of Einsteinium, the sample was prepared in Oak Ridge. It was contaminated with Californium, but with just 300 days, the fact that there was a delay of several months between the separation of the sample and the access to the synchrotron implied a reduction of the sample available of a considerable fraction. If a long-term proposal was in place, maybe this could have been avoided. So, of course, studying this kind of materials requires a very good organization and scheduling and so on, and synchronization of the scheduling.
Yeah, exactly. Now, perhaps the last question before we go to Luigi, because we do have a little bit of time, just to let people know, it was not mentioned actually that Caspar Peterson's talk, which is supposed to be 11 o'clock this morning, has had to be cancelled. Unfortunately, Caspar Peterson's wife has been taken to hospital after giving birth about 10 days ago. And so I don't know the situation today, but this cancellation was done just yesterday, I believe. So we do have a little extra time. So the only question I'd like to pose to Roberto now, before we get to Luigi's talk, is what's your feeling about this surface sensitivity? Because we are seeing now in the resonance technique, we are seeing, and Andrea will perhaps address this also, I suspect she is mostly working at the M edges, which of course couple directly to the 5F states. And we also have the N edges, which we've shown in the RICS. If you have a suitable sample, you can get a clear measure. But there are people working at the O edges. The O edges are only 100 electron volts. Now, the NICS work that Martin Sandeman will talk about is, of course, using higher incident energies. But people are actually doing experiments with incident 100 electron volt beams. We are very worried about the surface effects that happen there because, as Roberto said, your sensitivity is now down to certainly less than 5 nanometers, maybe only 1 nanometer.
Yeah.
Do you see that as a major problem for the soft spectroscopy?
It is certainly a challenge, especially for materials so reactive as actinides. It's not a case that we only have results on uranium dioxide because it was already oxidized. But other attempts for studying other compounds have failed. So a spectroscopy like soft risks or already at the N edge, at the O edge, I think would be extremely challenging. But this needs the development of sample chambers in ultra high vacuum and extremely good care in the preparation of the sample. Otherwise, I'm afraid that what the people will get is just a re-examination of uranium dioxide surfaces. So we have experience on this in our laboratory where we do photo emission spectroscopy. These experiments must be done in ultra high vacuum of the order of 10 to minus 10 because the reactivity of most of the elements and of many compounds is too high, and it's enough to have trace of oxygen or water to degrade the surface. And you can follow this immediately using photoemission spectroscopy techniques.
And in fact, in that, I'll just follow up on Roberto's remark by saying that this work in Karlsruhe also showed in the old days that you could actually get oxygen coming up from the inside the block sample. So Thomas Kuder, who was the physicist in charge of this, he finally developed a method to make thin films. These weren't epitaxial films, but thin films, because with thin film, you had no bulk source of oxygen. And that's, so I think this very low energy work, I agree 100%, Roberto, is really pushing another frontier, if you like. And of course, it can be perhaps very powerful in the future. Okay, well, thank you, Roberto, very much for that stimulating talk.
Thanks to you.
Things. And we now turn to actually 2 talks on inelastic scattering.
Okay, can you see the screen? Let me now just make
Yes, I can see it, yes.
Let me make this smaller. Okay, yes, thank you, Jerry, for the introduction. And I also would like to thank the organizers for organizing such a nice workshop and to give me the opportunity to present our recent results. Let me just go to the torch. I think that's nice. And now you can see it better. So these are our recent results I will talk about today. And this are X-ray studies on where we compare uranium M to silicon-2 compounds. And I hope at the end of the talk, you will see that this concept of uranium 5F electron duality is a good concept for the description or for the understanding of these materials. This project is a joint effort of University of Cologne and the Max Planck Institute, and I'm listed here the main players, and especially I would like to point out the name Andrea Amorese. But there are, of course, many others involved in this project. These are all the sample makers and sample making groups. Also, the beamline scientists should be mentioned. It's the new data I will be showing today. We're all taken at Petra 3 in Hamburg, but I will also show and present some older data that were taken here at ESRF on ID20. If simulations are shown, they were performed with a full multiplet code Quanti by Maurits Havercourt. Thank you. So the topic, it's about, or it's related to the hidden order in uranium ruthenium to silicon-2. It's an old problem. Uranium ruthenium to silicon-2 is an intermetallic uranium compound. It's a heavy fermion, and it exhibits 2 transitions. Here I show the specific heat versus temperature. It has a transition at about 17 Kelvin to some ordered state, and another transition into a superconducting state at about 1 Kelvin. And the mystery is about this transition here. it goes along with the formation of tiny antiferromagnetic moments. They're really small, and they're too small to account for the loss of entropy here. Therefore, accounted to a parasitic phase, and the nature of this order here is still a mystery. It must be some type of multipolar electronic order that goes along with the change of Fermi surface, but there are many suggestions what type of order it might be. But this is a question or a discussion I don't want to enter today here. I'd rather refer to these review articles. The most recent one is just in press, but already available on arXiv. So now to our study. It's a comparative study of isostructural compounds like ruthenium to silicon 2. And we are looking at compounds that have very different ground states. We have here our uranium ruthenium to silicon 2 compound. This is the hidden order compound with its transitions. We're comparing it with a Pauli paramagnet, uranium ion to silicon 2. It shows enhanced Pauli paramagnetism. It doesn't order down to lowest temperatures. And we have chosen the nickel and the palladium compound. They are also, the two of them are isoelectronic, and they have very high antiferromagnetic ordering temperatures and very large ordered magnetic moments. All four compounds in common they have the same crystallographic structure, and they have the same, if they order magnetically, they have the same ordered magnetic structure, that is ferromagnetic planes that couple antiferromagnetically along the C direction. To understand the physics of these materials now, we want to know the degree of itineracy. And that, of course, is a subject of spectroscopy, and there are many spectroscopic works have been done in the past, but you see here, there are results between a configuration of an F2 or an F3 configuration and anything in between. So all these studies, after all, have not been very conclusive. And this is why we decided, well, we are not aiming at an absolute filling of the 5F shell. No, we rather look at a relative 5F electron compound. And this is why we are comparing here these isostructural compounds with very different ground state properties. However, even then, we have to make sure they all have the same ground state symmetry, because the ground state symmetry is important for the way the ground state couples to the conduction band. And also, I think Sergei Buturin will talk more about this, the fingerprints on your spectroscopic data on the spectra depend on the ground state symmetry. So if you really want to compare and get a relative F electron count, we have to make sure our compounds have the same ground state symmetry. And that we are investigating with NICS. This is non-resonant inelastic X-ray scattering. Roberto already spoke briefly about the general concept of it. It's a photon in, photon out technique. We do some energy transfer for a core hole excitation, and we are looking here at the 5D to 5F transition. So really probing the 5F states. The nice thing is it's non-resonant. So quantitative modeling is not so difficult, it's possible. We don't need to cleave, because with 10 kV, we are bulk sensitive. We don't need UHV. This is all very nice. But for us, most important is that we can reach the large momentum transfers up to 10 reciprocal angstroms. Also something you have seen before by Roberto. These are Roberto's data on a polycrystalline uranium dioxide sample. Its intensity versus energy loss. Here at low momentum transfers, you have a very broad OH spectrum. It looks almost like an X-ray absorption spectrum. And if you go to the high momentum transfers, you have this extra excitations at lower energies further away from the continuum states, and that's why they're more excitonic. And these we can model very nicely. And we can use actually in order to do, for example, a single crystal experiment. If you now look at the momentum transfer relative to a certain crystallographic direction for tetragonal material like the uranium M to silicon 2 compounds, of course, we pick the 001 and the 100 in the plane, we can get access to the ground state symmetry like in a linear polarized X-ray absorption experiment. We simply exchange the momentum the direction of the electric field vector in X-ray absorption by the direction of the momentum transfer. And this here is a simulation, a quanti-simulation of the 7 states, crystal field states of uranium M to silicon 2. And you see the 7 states actually have very distinct polarization dependencies. And this is an experiment we performed some years ago here on ID20. of uranium ruthenium to silicon 2 at the uranium 045 edge for these two directions. And we see actually a huge directional dependence, the biggest actually possible according to the simulations. And we could index it only with the gamma 1,1 very much on the JZ plus minus 4 side, or the gamma 2, which is also a plus JZ plus minus 4. So we clearly can say the ground state symmetry of uranium ruthenium to silicon 2 is a gamma 1,1 singlet or a gamma 2 singlet, or of course we cannot distinguish in case these two states are very close in energy, that we would call then a quasi-duplet. In case you're wondering why I'm only comparing it here with this ground state symmetries of a uranium 4 plus and F2 configuration, then please look at these pseudo-isotropic data. They were constructed from the different directional dependent data. The uranium ruthenium to silicon 2 is here, this purple, are the purple data. And then the uranium cadmium 11, which is sort of an F3 type intermetallic uranium compound, has a very different line shape. And we can model it. Here, Martin Sunderman did the simulations, and we can model the uranium ruthenium to silicon to isotropic data very well with an F2 configuration and the uranium cadmium 11 with an F3. So we really can distinguish very well. And we in NICS clearly see the F2 ground state and the F2 ground state symmetry. And now let me come to the comparison of our four materials, the iron, the ruthenium, the nickel, and the palladium. And the iron, nickel, palladium data were taken on PR1 at DESY, the NICS beamline there. These are the ruthenium to silicon data from ID20 that I've shown you before. And at the bottom, the difference plot. And here are now the data of uranium nickel to silicon 2 and uranium palladium to silicon 2, the two antiferromagnets. If you compare this here with the ruthenium to silicon 2, and also we look at the difference plot, you have to agree that it looks pretty much the same. There's not much happening. We're comparing it with the nickel to silicon 2. Also there is not much happening in the range, energy range of the 045 edge. Only here in this energy range, we see a difference, but this is the nickel M1, a strongly dipole forbidden line, but of course we are in the beyond dipole limit. It's a nice proof actually that we are picking up beyond dipole scattering. We are now comparing it with the iron to silicon 2 sample. Also here in this polyparamagnet, we still see multiplets. And if you look at this energy range, it's again very much like the three other samples, only here it's different, but this is because here we are picking up the iron M1, which is underneath the uranium 045. But limiting the comparison to this part of the spectrum and comparing all these three other compounds, they have to say they all have the same ground state symmetry, which, as I've shown you before, is the gamma 1,1 singlet, the gamma 2 singlet, or we can't distinguish the quasi-duplet. You know, may wonder, I'm telling you, we have singlet ground states, but we have antiferromagnets. How can that be? Because indeed, a singlet state does not carry any moment. Only the duplet states do, but the nickel to silicon 2 and also the palladium to silicon 2 have really large ordered magnetic moments. Well, that can be if you accept that we have to deal with induced magnetic order in the presence of a quasi-duplet. If you have two singlet states, for example, these two singlet states, relatively close in energy, closer in energy than an exchange interaction would be, then we could have any ordered magnetic moment between 0 and 4 magneton. And that would accommodate actually these large moments. So this is a very nice confirmation that our assignment of symmetry is right. I mean, these two singlets could also give rise to a quasi-duplet, but the moments would be smaller, and of course the doublets would account up to 3, but that we really can exclude from our NICS data. So with this, we have settled the ground state symmetry. It's the same for all four compounds. And now we come to the relative 5F electron count, and this we are looking at with HUXPAS. HUXPAS is hard X-ray core level photoelectron spectroscopy. Hard X-rays in order to be more bulk sensitive. These experiments were performed at the end station of PO1, PO9, excuse me, that then was moved to P22, also at Petra 3. We came in with 6 keV incident energy, but nevertheless, photoelectron spectroscopy is a surface technique, even when you use hard X-rays, so that we have to cleave the samples, which is often a problem, but we were lucky that radio protection at DESY allowed us to cleave these materials, the uranium samples, but the demand was that they never should be exposed to air on the DESY premises. And this we can do by coming actually with our samples in a load lock. We are bringing, this has been designed at the Max Planck, we are bringing a cleaving chamber that then is mounted to the end station before the experiment, and it's been dismounted after the experiment, so that we fulfill the radio protection demand here, and we are not leaving behind any cleaved crumbs of uranium. So even DESY is an open site, we are allowed to cleave uranium samples. That is very nice. And here is the first core level spectrum I'm showing you. I'm showing you normalized intensity against binding energy, and I'm showing you here in blue the uranium cadmium 11, again, our F3 type uranium compound, and uranium palladium 3 that Roberto already mentioned is the F2, or the intermetallic uranium compound that is meant to be closest to an F2 uranium in red. The data have been background corrected, so we have subtracted an integrated background, and they have been normalized to the integrated intensity here in the region of the 4F core level. They look distinctively different in HuxPES. And if I'm now overlaying the uranium ruthenium to silicon 2 data, core level data here in gray, our interpretation is the uranium ruthenium to silicon 2 has features of both, of the cadmium 11, but also of the uranium palladium 3. Hence, it is intermediate valent. It is somewhere in between F3 and F2. And now let me come to the comparison with the other materials. Again, I'm showing the uranium ruthenium to silicon 2. These are the same data as I'm showing here. It's only a sort of spread Y scale. And now I'm showing you the uranium ion to silicon 2, the Pauli paramagnet. And what we see is actually we see more intensity here. And this is where the cadmium 11, where the F3 is more pronounced. So we have a shift from F2 to F3. We have less intensity here and we have more there. And now let me come to the antiferromagnetic compounds, the nickel and the palladium. And we have a successive decrease here, but increase there. So what we are seeing is we are seeing a successive decrease of intensity from more F3 to more F2 in the sequence from the Pauli paramagnet via the hidden order to the two antiferromagnets. All compounds, of course, are intermediate valence because they all share the features of both the palladium 3 and the cadmium 11. We also can say, because we know they all have the same ground state symmetries, any changes in the spectrum can only be due to changes in the configuration that cannot be due to different fingerprints of the ground state symmetry. Hence, we figure we are seeing in that sequence, as we see the decrease of 5F shell filling, we are seeing a decrease of 5D hybridization, and that very much agrees with the calculation of the density of states by Andrea Amorese that I'm showing you here, again for the iron, the ruthenium, the nickel, the palladium, in red, the uranium 5F states, and in color, same color coding, the respective D states. And what we're seeing here is the more F3 we have, the closer are the D states, the more they are overlapping actually, and the broader also the 5F states. So we go from the uranium iron to the ruthenium, here we're going down. We go to the nickel, we're going down, and we're going even further away, we go to the palladium, which has here the lowest, sort of F3 and the most F2. And with this, I'm basically at the end of my talk. I think I have shown you that we are on top of the ground state symmetry. We're finding a gamma 1 singlet, or rather a quasi-doublet that actually can accommodate the large ordered moments that all four compounds here, the iron, the ruthenium, the nickel, and the palladium have in common. All compounds are intermediate valent, and we find a decrease of FD hybridization in this sequence. You know, I wonder why I'm telling you that here we're seeing the uranium F2 symmetry, whereas I'm telling you, well, the compounds are intermediate valent. Is this a contradiction? No, it is not. It is not a contradiction because NICS, the non-resonant scattering, is like an X-ray absorption here at the O edge. So X-ray absorption, like for example, the M edge, is actually sensitive to the lowest configuration. And this is here the F2. So in all compounds, the F2 is the lowest configuration, and that then couples with an F3 that is slightly higher in energy. However, the photoelectron spectroscopy is sensitive more to the hybridization effects and therefore sees more the non-local effects. So we are seeing the local effects in NICS and we're seeing more the non-local effects in HUXPES, and that we think fits very nice with this ansatz or concept of dual nature of 5F electrons that tells us that, or this was a concept actually from Gertrud Zwicknagel and Peter Thalmeier, that they developed here for these heavy fermion compounds, that two of the electrons are localized, and it's the third one that is more itinerant that is responsible for the heavy fermion properties. Being so far, we thought we can now attempt the systematics of these uranium M2 silicon 2 compounds that we have investigated. I show you here the F2 Doniak phase diagram, temperature versus exchange interaction, here the antiferromagnetic regime, the Fermi liquid, and the quantum critical point. And we are putting the ion, the Pauli paramagnet, here in the non-ordering regime, the two antiferromagnets here, and the ruthenium very close to the quantum critical point, where often superconductivity is observed in other materials. And I mean, funnily enough, it's the ruthenium which is the only one exhibiting superconductivity. And with this, I would like to thank you for your attention.
Okay, thank you. Thank you very much, Andrea, for a very, very nice presentation and some interesting ideas. Now, although we still have a lot of participants, we don't have any questions and answers. Oh, here's one that's just come. So that's very nice. I have to read it out.
Maybe I go out of this sharing, yeah? It's maybe better.
Okay,
Yes.
well, that's good. And this question is from Etiri Smabatitsi. I can't pronounce that name. Thanks for a great talk. My question is rather general. Do you think there are more hidden order materials and we just haven't found them yet? Or is uranium ruthenium 2 silicon 2 so very special?
Oh, Cherry, you're asking a very difficult question.
It's not me.
I haven't across others. I mean, there are certainly other materials that have non-dipole order, and I think it's all about a 9-dipole order. And it's a very complicated multipolar order that has not yet been determined which type of order it is, but there are certainly more multipolar order materials, yes.
Right, well, in this particular case, you know, Roberto and I have been struggling with uranium ruthenium 2 silicon 2 for quite a long time. And despite great enthusiasm from some of our theorist friends, we have not found any of these peculiar orders that we found in neptunium dioxide and uranium dioxide. So it's really a challenge. And of course, one of the problems is as you get further out in the multipolar order scheme, the cross-section falls very substantially. So in that respect, it may be that the synchrotron intensity increases, which we've seen already with the EBS, and we will see presumably also with some of the laser, 3-electron lasers. That may open up a new field when you get down to these very small cross sections.
Yes.
Actually, Andrea, the question I have to you is perhaps a little more simple. It goes back to neutrons. Do you have this quasi doublet state, particularly in the uranium palladium 2 silicon 2, which seems to be the most localized and most nearly F2, you should be able to see some kind of crystal field transitions with that. Have you actually done those experiments? Because I remind you that in uranium palladium 3, you can see crystal field transitions.
I know. Actually, it's something I've been thinking about. We have not tried it.
Okay.
We have not done it. We have a small single crystal. I'm not sure it would be sufficient for neutron scattering, but that maybe is worth trying. Yes.
Yeah,
Whether we could pick up some excitations.
The other technique is, of course, to try it on the Rix spectrometer.
Well, there, Martin will say a few words.
Yeah, we were together at Diamond, and I know that you tried. Was it the nickel sample you tried at Diamond?
We tried the nickel, the antiferromagnet, yes.
And you saw nothing. But so just for the people who perhaps don't realize the question here, these Rix experiments, which in some sense complement the neutron experiments, they have two big drawbacks when you go into intermetallic systems. The first one is that you have, once you have the conduction electrons, you get your hybridization, which Andreas talked about, and so you get broadening effects in both in the neutrons and potentially also in the Rix experiments. And the other one, which is specific to the Rix, is the surface sensitivity. And we still don't know, and that's why I made the question to Roberto about the N edges. We still don't really know the answer to that, whether it's the surface sensitivity or whether it's the hybridization. So there's still a lot of open questions on that. Any comments?
I mean, sure, the actinides are heavier than the rare earth, but I mean, in cerium, for example, we get a fantastic signal, no?
Yeah, that's right. That's right.
It's not a problem. What I find is and I will certainly, now I'm asking questions, maybe to Roberto, because we are certainly interested in continuing, I mean, this project, and we always need more samples. So I certainly want to investigate more the NICs, to what extent we are sensitive to the valence states in NICs.
Yeah.
The ground state, because I said it's very much like X-ray absorption, like the M edge, and I think this is why the M edge, where you and Christina looked at, you see that the uranium palladium 3 and the uranium ruthenium to silicon 2 are on top of each other, something you would also expect to see in the NICs.
Yeah.
Where it's very different in the photo emission.
Right, right.
So that is something we want to keep working.
Yeah. Okay, well, thank you, Andrea, very much. So that brings us actually to the end of this session. So I'd like to thank and congratulate all the speakers on very fine talks that we've heard this morning, 4 talks. And now I hand it over back to Christina or Fabrice, because I think the next session will start at 11:40, but I'll let them say that. Are you there?
Yes, hi.
Yeah, thank you. Hello. Thanks for giving me the opportunity to speak. So let me share my screen. So now you should be able to see my slides, I guess. Yeah, so thanks for the organizing committee to giving me this opportunity. This was quite a surprise because as I advertised it in the abstract, I'm going to bring more questions than answers. So in that respect, I think the question and answer sequence at the end might be upside down. And I should compliment them for the very good scheduling, because by this time of the day, I think everybody's got their brain fried up like mine. And they are looking forward to lunch. And fortunately, this talk is going to be rather short and rather simple in terms of theoretical concepts as compared to what we've seen before. So I'm going to talk about uranium ruthenium to silicon 2, which has been discussed quite a lot this morning. And I should thank the previous speakers for introducing this topic very well. So like like most of the studies, we were focusing our work on the hidden order phase, but it brought us to some other results, which I'm going to show you. So the people who participate to this study are Jonathan Buot, who's currently at the University of Bristol, Didier Vermeil, who's a beamline scientist at XMAS, at the British CRG at ESRF, Steve Collins and Gareth Nisbet, who are beamline scientists at Diamond, where the data were taken. Elena Ovchinnikova and Vladimir Dmitrienko, who brought us some ideas that actually led to the proposal and experiments that we did. Mario Measson from Institunel, with whom we had quite a lot of discussions, and Dayaoki, Georg Nebel, and Jean-Pascal Brison at the CIA Grenoble, who provided the samples, and with whom we had also quite interesting discussions. So I'm just going to give a very brief overview of this system because it has been discussed quite a lot this morning. I'm going to discuss the search for multiples that we did in the hidden order phase, and I'm going to present the sample preparation and experimental details, and then I'm going to move to the results. So we're going to have short results on the story of the fourfold symmetry breaking. I'm going to talk about the parasitic antiferromagnetic phase, and in addition to that, I will talk about chemical and structural characterizations, which are interesting regarding to the results we had. So very briefly, as you know, uranium ruthenium 2 silicon 2 has been the subject of many studies for the last 35 years. The reason being that it hosts a hidden order below 17.5 K, which was first observed on the signature of on the specific heat, and it's kind of a massive signature. And so far, there has been no explanation to explain such a strong signature on a specific heat, despite many theories and experimental attempts. So importantly, the crystal structure as a space group I4/MM, so that means it's a body-centered tetragonal lattice, and the uranium atoms are hosted by this cage made of ruthenium and silicon atoms. Yeah. So for a more complete view of this topic, you can see a recent review here, which is actually published. So there are many open questions on the hidden order phase. So first, one can wonder if there's a translational symmetry breaking. So in the current state of the art, most people think that it is the case, and that there is probably a propagation vector which is related to the Fermi surface nesting at 001. So that's, I think now this is pretty much established. What is more debated is the case of the fourfold rotational symmetry breaking, which has been proposed in the early 2010s. But that's still debated because it has not been really observed many times. The time reversal symmetry breaking is also very much debated. So related to that, many types of orders were proposed. So there could be magnetic multiples, but of which order? Electric multiples. And then what can wonder if the 5F electrons are localized or itinerant. So we've just seen that the most likely explanation actually is that they have a dual character. That means that there are two 5F electrons which are localized and some others are itinerant. Then some people propose that the hidden order phase could be related to a valence transition, related to Fermi surface gaping also. And interestingly, there is also a competition with other phases, and in particular a long-range dipolar antiferromagnetic phase, which has been seen in all samples, even in the so-called best ones. And it's been characterized as a function of temperature, operation, chemical substitution. So there are many proposals to explain this hidden order, but none of them has been really confirmed yet. This could be, for instance, an anti-toroidal vortex, a magnetic Dautria contemporaire order, an electric Dautria contemporaire order, and so on. So our initial motivation was to look for this particular order, which has been proposed by Vladimir Dmitrenko, which is an anti-toroidal vortex. So the idea is that each uranium site hosts some sort of vortex-like magnetic distribution, which circles around, well, in two hemispheres, and each hemisphere will circle around the z-axis in opposite directions. And so the idea behind that is that this kind of multiple would be the lowest rank multiple you could have, which is compatible with time reversal symmetry breaking and the non-breaking of the fourfold axis. So these anti-toroidal vortices, they could order in a unit cell either ferro or an antiferroic order. So we wanted to see if we could look for that. So how can we detect multipolar orders with resonant X-ray diffraction? So your best hope is that you're gonna observe that you have an antiferroic order, because in that case you could observe this antiferroic order at forbidden reflection of the unit cell. So here, because it's a body-centered lattice initially, and if we have antiferroic order with propagation vector 001, we could have pure antiferroic reflections appearing at the forbidden reflections. And the reason why is that when you use resonant X-ray scattering, you are enhancing your sensitivity to the anisotropy of the tensor of scattering. That means that when you're non-resonant, you essentially see a spherical charge distribution, whereas when you are resonant, you can see anisotropic distribution of the valence shell. And if your corner and the body center sites have let's say different anisotropies, you would end up with something at these forbidden reflections. But this is fairly weak, and of course it depends on the edges that you are using. So initially people were looking at the M4 and M5 edges of uranium, but unfortunately on this in this case you look essentially at dipole transition, and in this case you can probe multiples up to rank 2 only, and the quadruple transitions are very weak in this case. Because they would probe a 6G state. So to have a chance to probe multiples of rank up to 4, you need to go to quadrupolar electronic transition, and they are sizable, let's say, although weak, at the uranium M2 L3 edge or uranium L2 L3 edge. And so this has actually been attempted and published in this paper, but at the time when we were going to do the experiment, this was not published yet. So that's why we had the same idea actually. So how can you identify the multiple that you measure in case you're able to measure it? You can identify it through the polarization and the azimuthal dependence of your diffraction signal. So the idea is that if you're measuring a diffraction peak in direction Q, you can change. Well, you can make a polarization analysis of your scattered signal. So either keeping the same polarization as your incident beam, or probing the rotated channel, and you can also rotate your crystal around the diffraction peak, and you will see different symmetries of your signal depending on the multiple you can probe. So this has been nicely described in this paper actually, although experimentally they didn't find anything, but this is the theory. So I'm coming now to our experiment. So we had samples provided by the CA Grenoble. So there are samples grown by the Srokalski method. and cut using a spark cutter, and then re-anneal for 3 days at an ultra high vacuum. So the group of there has a large experience in growing these crystals, and our particular sample was not further characterized in the lab, but based on their experience, they expect that the figure of merit, which is used in this case, which is the triple R coefficient, which is a ratio of resistivity between the power, the power phase and the resistivity at 1.5 Kelvin is around 40 or 50, which is rather good for this kind of growth mode. But it's if you now look at the best samples which are grown by flux method, they go up to 300 or something like that. So it's much better. So this coefficient actually it's a very good figure of merit because it includes chemical and structural defects that your sample can hold, which would affect the electric resistivity. So our sample is a cubic sample of 1 millimeter of size, and it's while looking at scanning electron microscopy, it's fairly homogeneous, I would say. I will come back to this later. So the experiment was done at beamline I16 at diamond light source, and I would like to emphasize the fact that in a single experiment we were able to explore very different ages. So we looked at 2 types of uranium ages, so the L3 age at 17 kilo electron volts, but also the M ages around 3.5 kilo electron volts, and we also went to the ruthenium L ages by curiosity, but you know, I mean, it's not so difficult over there to go there, and this is at 2.8 keV, so it's rather low energy. The experiment was performed at ambient pressure without magnetic field, and it's a rather standard setup, let's say, for resonant X-ray diffraction, with the sample embedded in a cryostat here. And we used an array detector, which is a Pilatus here, mounted on a detector arm, and also in some cases we used the polarization analyzer, which is mounted over there with a vortex energy result detector. So, well, like everybody else, we had negative results on the multiple orders. No, not really a big surprise, you would say. So we looked at many things. We looked at many forbidden reflections of the HKL order type, and there was really nothing over there. We also looked at a loud reflection in order, you know, in case the signal would be a ferroic order. But to do that, you need to get rid as much as possible of the vastly superior charge scattering. So for that, you would scatter in horizontal geometry and use the polarization analyzer to reject much of it, but we didn't see anything. We did large L scans also to look for other possible other propagation vectors, but didn't find anything. We did similar work at the ruthenium L2-3 edge, which has not been done by anybody else, I think, before, just in case there was something to see over there, but we didn't really see anything new. So I'm just going fast to this. About the 4-fold symmetry breaking, we checked that. So Tonegawa et al., they observed a splitting of their 888 reflection in the hidden order phase, which they attribute to the 4-fold symmetry breaking, because if you have 4-fold symmetry breaking, you will have different domains, and they would provoke a peak splitting. But we didn't see any sign of peak splitting on the reflections we measured. One of the explanations could be that it's related to the RR of the sample, so the quality of the sample, let's say, because in their case they looked at 2 different samples and they saw the peak splitting only in the highest quality samples. So that's not really solving the problem. At the uranium M4 edge, we saw the parasitic antiferromagnetic order, which is seen in all the samples, even though it's small. And we could confirm that the spin is aligned with the C-axis. It matches very well with the intensity of the diffraction peaks we had. Also, the temperature dependence is also in agreement with what can be expected from that. So now what was surprising for us is that we did a map of the sample. We did both on the charge peak, which is here, the 004, which is somehow almost homogeneous, I would say. And we looked at the magnetic peaks, the 104, which is on contrary very inhomogeneous. So that was quite surprising. And we did cycle the temperature above the hidden order transition. And when we come back to the hidden order phase, we find the same chemical, well, the same magnetic map again, which seems that this parasitic phase seems to be pinned somehow. So in more details, you can look. We sampled the sample. I can show you some rocking curve, and you can see on the charge peak, it's very homogeneous everywhere you look at the sample, except here, because here there's clearly a notch in the crystal. But then if you look at same positions for the magnetic peak, you can see that the intensity and the width vary quite a lot. I'm discussing only this broad peak. This is some spurious peak here, which I don't know where it comes from. So to complement this analysis, we did some Edx analysis in the lab to see if there was a departure from stoichiometry or some contaminations from other elements. And so basically we did this analysis along two perpendicular lines separated at points separated by 150 microns each time. And you can see all the scans are overlaid together, and there is basically no significant difference as much as we can say with this technique. So there is no obvious inhomogeneity from the chemical point of view. Another thing that was interesting, which we saw by X-ray diffraction at the synchrotron, is that we saw some additional peaks that were not expected. So if you look at this L scan here, you can see that there are small shoulders appearing beside the main peaks here, and these shoulders sorry, they are consistent with the phase that would be which will have a C lattice parameter 0.4% larger than the main phase. But it grows coherently with the main phase. What is also interesting is that if you look at a local HK map around one of these peaks, you can see this sort of streaks here that goes towards the HK direction, but also the HH directions. So these are attributed maybe to domain boundaries of this phase. But so unfortunately, we could not check the space homogeneity of this phase on the samples because we did not have time to do that. So I'm coming to the conclusions, and as you see, I have left many open questions. So we didn't see any multiple order by resonant X-ray diffraction at the many edges we looked at. We didn't see also any evidence for the fourfold symmetry breaking. But what we saw is that the parasitic dipolar antiferrometric order is very inhomogeneous on the sample, despite the fact that we didn't have a clear sign for strain inhomogeneity or chemical inhomogeneity. And the other interesting finding is that we found in our sample some structural minority phase, which grows coherently with the main phase and has a slightly different C lattice parameter. Something that I haven't commented is that this phase is probably also body-centered because we don't see any peaks close to the H plus K plus L or the superlattice lattice reflections. And we see grand boundaries along the 100 and 110 axis. We could not check the space inhomogeneity. And so with that, I thank you for listening, and I'm looking forward to your questions and advices. Thank you very much.
Thank you, Guillaume. I look the question answer to see if there is any.
Can I ask a question or make a comment, Luigi?
Yes, yes, of course.
Yeah, Guillaume, nice talk.
Really, as you introduced, I am a chemist, and it's quite a challenge for me to have a talk where mostly spectroscopists and physicists are hearing me. So today I would like to give a lecture on chemistry behind actinide, colloids, and nanoparticles, mostly with the application to environmental behavior, nuclear waste management, and related things, and how we use different spectroscopic methods, mostly spectroscopic methods based on the synchrotrons that we are doing in collaboration with the SRF and many research institutes. So I would like, it's my pleasure to start with the very general thing. So today, this year, 2021 is a special year for all the radiochemists, all nuclear chemists, nuclear physicists, and many others. So it's 125th anniversary since the discovery of radioactivity that was done in 1896. So this is probably the only science, the nuclear science is the only science that have the exact month, exact date, and exact year of the birth. So it's nothing about other branches of sciences like inorganic chemistry or polymer chemistry or whatever. And this year we also celebrated the 80th anniversary of discovery of plutonium. So my talk today will be mostly focused on plutonium chemistry and some analogs. So the general motivation, the global motivation of the studies and of my lecture is actually linked with the aim of decarbonization of the atmosphere that was proposed, that was aimed by OECD to result in 50 grams of carbon dioxide per 1 kilowatt hour of electricity. And according to different forecasts done by OECD, International Energy Agency, by the World Nuclear Association, the share of nuclear probably would be increased, and because nuclear is a concentrated source of green energy. But the problem is that we still have very important remaining issues related to nuclear. One is the safety of geological disposal of spent nuclear fuel or radioactive waste, depending on the strategy of different countries. And the second one is decommissioning and cleanup of contaminated sites. So that is extremely important for the countries like United States, former Soviet Union, and some European countries, and definitely Japan. So today I will talk mostly, or not mostly, but only about actinides and mostly on plutonium. So the reason is that if we see the radiotoxicity of the spent nuclear fuel and different contributions of different radionuclides to the toxicity of the spent nuclear fuel, we'll see that at the large time scale, we have mostly contribution from plutonium, from americium, and their decay products, including, for example, thorium-229. That is very important. Since this means that for safety assessment, for prediction of migration in the long-term scale, we need to learn, we need to know the chemistry, we need to know the speciation of these elements. So just for the broader scientific auditorium, just 1 minute to remind you that plutonium is the element of surprise. So this was the title of one review paper published by Greg Chopin, who was my teacher when I was staying in the United States. Actually, he is one of the, this is important for me, he is one of the discoverers of Mendeleevium together with Landseberg. So the important thing that plutonium chemistry is really very surprising. So we have at least 4 oxidation states that could be in the equilibrium between each other. So in Purbier diagram, you can see these red dots where 3 redox states are in the equilibrium between each other. And depending if we are talking about environmental conditions, depending on the pH, EH conditions, we have the mixture of oxidation states, we have the transition from one state to another. And the important thing on the right side of the slide, you can see that this is the solubility of actinides in different redox states. So for example, if you have the oxidation of plutonium-4 to plutonium-5, you have a large increase in the solubility that is several orders of magnitude. So from relatively insoluble plutonium compounds like plutonium dioxide, we move to quite soluble, very soluble plutonium-5 species. The important thing that I would also mention in several examples today in this presentation is that plutonium could be studied also using the redox state analogs. If we are studying, for example, complexation of plutonium-3, we can use rare earth elements that are also trivalent mostly, and americium as a valence state analog. For plutonium-3, plutonium-4, we can use cerium-3, cerium-4. For plutonium-4, we definitely can use thorium and zirconium to some extent, but I would show that the chemistry is really somehow different compared between plutonium and thorium. For plutonium-4, 5, we can use neptunium-4, neptunium-5, and definitely can use uranium-6 as a model for plutonium-6. Also, I will demonstrate that the chemistry of uranium is even more complicated than the chemistry, particle chemistry of plutonium. So the first evidence is that particles are very important, colloids and particles are very important in speciation of plutonium. They appeared quite long time ago, even before 1999, when Annie Kersting published the paper in Nature demonstrating that plutonium is migrated far away from the underground nuclear test site, about 1.3 kilometers away, and the particles were responsible for transporting of this plutonium. And it was quite shocking because plutonium, as plutonium-4 is the dominant redox state, was considered as non-mobile. Then there is evidence for Mayak, that is a contaminated site in Russia, where it was demonstrated that plutonium is stick to different colloids, and also particles are very important for transporting plutonium to the far distances. So the motivation to study plutonium chemistry, plutonium interfacial behavior, and plutonium particle behavior is that there's even gap knowledge in the things like solubility phenomena. There's great number of papers, and the excellent papers published by colleagues in INE, in Karlsruhe, Volkenek, who passed away some time ago. They made an excellent solubility studies under different pH conditions, showing that the important thing is that plutonium that is equilibrated, that the solution that is equilibrated with plutonium dioxide, it always have a large contribution of colloids, of intrinsic colloids that are stay in the solution, that are stable. But unfortunately, and even they find out the log K values, so the thermodynamics is quite well studied. The problem is that we still there was the gap knowledge in what is this colloids are, what is the size, how stable they are, what is the speciation of plutonium in these colloids, if they're crystalline or they are amorphous, if there is some aging of these colloids, how they are formed, and what is the formation routes, etc. And there are many studies that are cited in this slides on plutonium colloid chemistry. So there is still we did not know at that time if plutonium-5 or plutonium-6 or plutonium-5 or plutonium-6 or plutonium-3 is introduced in plutonium O2 structure, colloidal O2 structure. So this was really the motivation of the studies that we are doing in the large collaboration, international collaboration between Russia, Germany, and France. So we do a lot of wet chemistry in Alpha Lab in Moscow, experiments with plutonium. Then we repeat some of the samples in Germany, in Helmholtz Zentrum Dresden-Rosendorf. And then we transport some of the samples to SRF, to some other synchrotrons. But most of the samples that I would show today, they are linked to the studies done, spectroscopic studies done at SRF, where most of the beamlines can accept the radioactive samples. The important thing is that due to the high brightness of the source, we can work with a very low concentration of the actinide. So this is very important for us because we always have to remind us that plutonium is radioactive, is toxic. So we need to minimize the handling of such samples. So there's a combination of techniques that we use. So certainly this is wet chemistry, kinetic solubility studies under different conditions, and then examination by different methods, very local methods like high resolution transition electron microscopy with selected area electron diffraction, with some very local things. And certainly the spectroscopic methods starting from X-ray diffraction, HERF, EXAFs, and PDF. So again, actinides are studied at all beam lines, and higher levels of activities could be studied at BM20, that is known also as a Roberto beam line. So data presented here, it was collected at these beam lines presented here, and also partly at Kurchatov Institute, at Mars beam line and Soleil, and at CAT-ACT beam line at Kara in Karlsruhe. So I'll start with the plutonium. So the experiment that was done in many different conditions, in many different ways, and different pHs, and also in the time scale, when we took different precursors. So we took plutonium-3, plutonium-5, and plutonium-3, 4, and 5 separately. Then we, in relatively acidic range, then we increase the pH, and we can see the precipitates that is formed quite fastly. And we wash this precipitate, and then we analyze this precipitate through different spectroscopic microscopic methods. So first it was C by ATM, that there is a lot of very small nanoparticles, so we can see their crystallinity. The size is about 2 nanometers in size. According to the selected area electron diffraction, we can see that this is plutonium O2-like particles that are formed. But we always have to remember that when we use TM or any local, very local method, certainly we can drop down to visualize as separate atoms, as you can see it in this image. But you always have to remember, you have a large sample that contains, for example, millions of different particles in there, and we can visualize only, let's say, tens, hundreds, maybe a little bit more particles. So this means that TM is not reproducible towards the characterization of the whole sample. That's why TM and any local measurements should be supported by spectroscopic methods that can characterize the sample, the whole sample. So we start with X-ray diffraction, and we can see that there's no amorphous contribution, that there's a broadening of lines, and the broadening is certainly because of the nano size of the particles, and the size were determined. The size is quite close to what we have from the TEM measurements, so this is a good thing. And the most questions that we can answer, they came from the examination using X-ray emission spectrometer that was built on the Roberto beam line that can support us with the methods like high energy resolution fluorescence detection, X-ray absorption spectroscopy, resonance inelastic X-ray scattering, X-ray emission spectroscopy, etc. So we can get the direct in situ information concerning the speciation of plutonium, about the local molecular environment. That is really very important for us. So this is one of the examples. This is the characterization of the samples of plutonium nanoparticles. So the interesting thing that we were asking for is there are some traces of plutonium-3 or plutonium-5 or even plutonium-6 present in the structure of these nanoparticles, probably on the surface of these nanoparticles. So we use L3H, that you can see there the spectrum depending, they're quite similar. So there's no great spectrum changes in this case. And we also have here the reference spectrum of plutonium, microcrystalline plutonium dioxide, and plutonium O2 calculated. The reason that is, even we have the admixture of some other oxidation state, that L3H is not that sensitive towards redox admixtures because 5F4 electrons are not involved in the L3H, compared with the with M4H, where we have 3D10, 5F4 to 3D9, 5F5 transition. So 5 electrons are involved, means that we are extremely sensitive towards the redox speciation, and we can define a very small amount of one redox state in the presence of the other redox state. So what we found here, that there's only plutonium-4, so we don't see any tracers of plutonium-3 or plutonium-5 in this nanoparticles. The EXAFS was done to characterize the local molecular environment, and you can see here that certainly the coordination numbers of plutonium is decreased because we're really, for 2 nanometer sized particles, the number of atoms on the surface start to be important, and the coordination number for the surface plutonium is different compared with the bulk plutonium. That's why we have the decrease in coordination numbers, and plutonium-plutonium contribution is also lower compared with the microcrystalline plutonium O2 references. The very powerful technique, again, that could be used to trace the long-range order of the nanoparticles, not only to determine the particle size, but to determine pair distribution is presented here. So this is a pair distribution function of this plutonium O2 nanoparticles. As you can see, again, this data supports the X-ray diffraction and TM measurements. We really deal with very small nanoparticles with the size from 1.9 to about 2 nanometers in size, independently on the starting redox state of plutonium and independently on the conditions how these nanoparticles were cooked. So this is some kind of a small conclusions concerning this part of work. Again, we have nanoparticles, 2 nanometer size nanoparticles. They are not amorphous. They are crystalline, that we can see definitely from TM and from X-ray diffraction and selected area electron diffraction. The crystal structure is similar to plutonium O2, and we have no oxygen splitting in the inner shell of plutonium nanoparticles. And this is only plutonium-4 in all cases, plutonium-3, plutonium-4, and plutonium-5 when taken as a precursors for preparation of these nanoparticles. The and the kinetics of this process is quite fast. So independently on plutonium-3, 4, and 5, we have relatively fast formation of these precipitates that are aggregates of this plutonium nanoparticles. This is in contrast if we take plutonium-6 as initial oxidation state. So very interesting thing that the kinetics in this case start to be much lower. I would show you in the next slides. And the examination of plutonium-6, when we take plutonium-6 as a starting solution, gives us the clue that we have some intermediate plutonium-5 solid state. That is a quite surprising, because plutonium-5 is not very stable. It disproportionates to plutonium-6 and plutonium-4, and very few plutonium-5 solid phases are known. So by again using high energy resolution fluorescence detection at M4 ages of plutonium and comparing the spectrum with their reference, we can see that indeed we don't see in the intermediate phase, we don't see plutonium-4, and this is definitely plutonium-5 that we have. The great job was done when we tried to learn what is this plutonium-5 phase is. So we took different known phases of plutonium-5. They are presented here, and we made average mass calculations versus experiment. So the upper spectrum is experiment, and this is the L3 ages of plutonium, and we analyze this A, B, C regions that are different for these different compounds because they are sensitive towards the structure. And you can see that there is the only plutonium-5 spectrum, model spectrum is a mixed carbonate of plutonium-5 and ammonia that corresponds to our experimental data. The important thing also that I already mentioned is that the kinetics of this process, the kinetics of formation of this intermediate phase is quite slow. So this is compared with plutonium-3, plutonium-4, and plutonium-5, that is few minutes that we have the green precipitate. So in this case, this could be up to several months. So the measurements that were repeated in 3 months, that we still have this plutonium-5 in the system. So this looks like as we start with plutonium-6 aqueous species, hydrated plutonium-6 aqueous species, then there is increase in solubility because we have the redox transformation to plutonium-5 and increase in solubility. We have this intermediate phase, ammonia, plutonium-5 carbonate, and then there is a slow decrease in solubility that is due to the relatively slow reduction of this intermediate phase to plutonium dioxide nanoparticles. So under steady state conditions, at the end of this process, we also have plutonium dioxide-like nanoparticles. They are also 2 nanometers in size, and they are also crystalline. Can we use thorium really as an analog to plutonium? So thorium have 0 electrons on the 5f orbitals, means that any spectral changes that we can see is only due to the structural difference, but not due to the redox chemistry behind some processes. So for thorium, we surprisingly found that depending on the concentration of the base solution, depending on the concentration of thorium, depending on the temperature, we have various particles with different sizes. They are all crystalline, they are all thorium dioxide, but the size is quite different. And depending on the conditions, we can cook the samples from about, again, 2 nanometers in size, very close to what we have for plutonium, up to, let's say, about 40 nanometers in size. If we hit the sample, we can get larger samples. We can get larger particles. We use EXAFs to characterize these particles, and you can see that the spectrum is changing. So the lowest spectrum is 2 nanometer sized particles. You can see that the thorium-thorium interaction is depressed, and you can see while we increase the particle size to 34 nanometers, so this thorium-thorium interaction is increased. And the coordination numbers is certainly in this nano region that is from let's say from 2 to 10 nanometers in size is different, is changing. So we have the with the increase of the particle size, we have the increase of the formal thorium-thorium interaction, informal increase of the coordination number of thorium. And also we, maybe not surprisingly, but what we observed from many independent measurements, that in this nanoparticle region, 2 to 10 nanometers, we have the changes of the lattice parameter that is due again to the number of surface atoms, and some that's not to be important when we are speaking about very small particles. And certainly the surface hydroxyl and carbonate groups, they also have some tensile effects. So the changing the lattice parameter, that is important again for this nano region. So the again, I would like here to show the very powerful technique that is PDF power distribution function that can give us the long range order nanoparticles and in the some hexamers that we see. So how the experiment was done? So we took thorium-4 sample, then we increased the pH. We have the hydrolysis, and before the particles are precipitated, we have some polynuclear species that are probably hexamers, and using PDF. We can make the feed component, and we can define, for example, under, as prepared sample dried only at 40 centigrades, we have 60% of this polynuclear species of thorium hexamers. We have about 24% of 1 nanometer size particles, 7% of 2 nanometer particles, and 7% of 3.5 nanometer particles. So this is a very powerful technique that can give us the information about the size distribution in this complicated mixture of different particles. When we increase the temperature, the particles start to grow, and we don't have any more the hexamers. We don't have any more polynuclear species. We have only a nanoparticle. So there's 24% of 1 nanometer particle, 2.5 is about half of the particles, and about 30% of the 5.6 nanometer particles. So this is very, very important demonstration of the ability of PDF to characterize complicated mixture of different nanoparticles and polynuclear species present in the solution. Then we have certainly M4Hs that is sensitive towards the changes of the structure. So, and we trace the changes in the C and D region, and you can see here, depending on the particle, we have the different we have the size effects that is shown in the C and D region. So size effects show up in these features, features C and D, and simulations based on thorium hexamer structure and bulk thorium-O2 reproduce these effects. So I don't have a lot of time, but still have several examples to show. So just one slide concerning uranium. So uranium dioxide particles, the behavior is even much more complicated compared with thorium. So this is actually not very surprising, because the area, the stability area in Purbye diagram, if we compare plutonium under neutral pH conditions, so plutonium-4 is dominating. So this is the major redox state compared with uranium, where we have both uranium-6 and uranium-4, and certainly uranium-5 could be present. So there's pretty much more possibilities for redox mixtures and redox changes in the particles that we have. So we made an experiment under nitrogen conditions under inert atmosphere with very low concentration of oxygen. We made transportation to SRF in the special cell, not allowing oxygen to get in there. And what we found is that certainly in the freshly prepared sample, this is uranium-O2 nanoparticles, the behavior is very close to what we have for plutonium. So this is 2 to 3 nanometer size oxide nanoparticles with only uranium-4 present in there. But when we have the aging, the first things what we found is that upon aging we have the oxidation of uranium-O2 to uranium-O4-O9 like particles with the presence of uranium-5 and uranium-6 in there, and this aging results in the increase of the particle size. So this is not like in case of plutonium, where we have this plutonium nanoparticles that are extremely stable in time. So we have the increase in size, and they are much more sensitive towards the beam damage that we also observe, and we have the oxidation of these nanoparticles under the irradiations. So the last example that I would like to show, maybe 2 minutes more, is cerium-3, cerium-4. So cerium itself is a very, very important material. So it's photocatalysis, pigments. It's even used in the medicine as an antioxidant. And the important thing that we were looking for is, again, as an analog for plutonium-3, plutonium-4, And when we have plutonium dioxide, for example, precipitate, if there is some presence of cerium-3 on the surface, if we go down to the nanometer-sized particles, what is the chemistry behind their higher reactivity and this antioxidant activity? Is it due to the cerium-3 present in the structure, or there is some other effects? So again, we made all these precipitations, we made the X-ray diffraction, the size, again, not like in case of plutonium. So the size was dependent on the concentration of cerium, and it was dependent on what we take as a precursor, either cerium-4 or cerium-3. So the size was quite different from, let's say, 2.8 nanometers up to more than 10 nanometers in size. So this is again not like in case of plutonium. So we made L3 ages for characterize the colloids, the particles there. So there is no evidence of cerium-3 in the structure of cerium-02 nanoparticles. So independently on the particle size from 2 nanometers to 8 nanometers, we don't see any presence of cerium-3 in the structure of these nanoparticles. This is different if we take the solution. So when we analyze the solution, depending on the pH, we have only cerium-3 in the solution. So this is very probable that we have reductive dissolution mechanism of this cerium dioxide nanoparticles. And solubility, we made the solubility measurements with a radioactive trace of cerium-141. And depending on the pH, for the first time, we made a very precise measurements of the equilibrium constants of this reaction. So at low pHs, we have the reductive dissolution. At the higher pH region, we have the oxidative dissolution, where we have cerium-3 in the solid phase and cerium-4 in the solid phase and cerium-4 in the solution. At the lower pH, we have cerium-4 in the solid states and only cerium-3 in the solution. The interesting thing is that we use different drying process, and we try to heat the samples, and the spectrum changed upon this changes of the sample. So what we think is going on, that upon drying and upon heating of the sample, especially for 2 nanometer size particles, again, when we have a lot of atoms on the surface, when the surface atoms start to be very important, we have the difference between, for example, as prepared very fresh samples compared with the dried samples, and say nothing about sample dried at 150 centigrades. So how we can explain it by the change in the surface and the effect of the surface hydroxyl groups that is different compared with as prepared fresh samples and dried at different temperatures. Very last slide. So not going to say a lot about this work, so it's a little bit far from nanoparticles, but also deals with the speciation of different radionuclides. So we analyze in collaboration with University of Umeå in Sweden different graphene oxides. So graphene oxides showed extremely high efficiency towards different radionuclides, because this is the graphite sheet that is covered with the oxygen-containing groups, and these oxygen-containing groups are responsible for binding of different cations. And we can prepare highly defect graphene oxides, or a lot of holes, holes enriched in carboxyl groups, and by spectroscopy and by calculations, we can learn what are the preferential groups to which different radionuclides like americium, like uranium are attached to. So the efficiency of these highly defect graphene oxide are much higher compared with the normal graphene oxide. So at the end, I would like to acknowledge all the collaborators. So this is the names and a lot of students who are working on this project. Certainly, I would like to acknowledge SRF for the beam time allocation, and also capability to bring plutonium to all SRF beam line, like ID26, ID15A, and many others. I would also like to urge the audience to stay on the air and to listen to very interesting talks that we will have after mine on plutonium nanoparticles from Matthew Birov, then on the Herdon Vrix on actinide science by Tony Vitova, EXAFS and data analysis by Thomas Dumas, and by Sergei Butorin on theoretical calculations in higher resolution spectroscopy data. So thank you for your attention.
So I have two examples to show today. One is related to uranium mining and uranium separation process in those mines. And one is related to plutonium separation, which happens on some alternative Purex process. Okay, so I will directly go to this AMEX process that is used to produce 50,000 tons of uranium per year. It is based on the separation of uranium from acid sulfuric leaching of uranium ores. And in this process, you use a trialkylamyl molecule that you have in an organic phase to extract specifically uranium and purify it. And so there is some questions that one may ask about this process and that are not answered yet, which basically is what are the reactions that we are doing in this process? What are the stoichiometry of the complex, both in the aqueous and the organic phase? And this is how EXAFS can help with that. For the aqueous phase, there is nice publication specifically by Christoph Hennig, who is working at the ESRF, who some years ago published this data and shown that for uranyl sulfate complexes in aqueous solution, you can easily identify, I mean, it's a convenient tool to identify uranyl sulfate complex. And you see that you have between 0 and 2 sulfate anion around the uranyl. And also with the help of DFT models, he was able to show that you can discriminate between the two monodentate or bidentate sulfate group coordination mode. So what is going on if you jump to the organic phase in triactylamine? And here is what you measure if you do that. So this is our result that we measured at the Mars beamline. And on this spectra, the black one are the experimental spectra, you write right after measurement, you see that you have a huge peak that arises in the second coordination sphere of uranyl. And this is related to an increase of the amount of sulfate in the uranyl coordination sphere. And if you try to fit it with different model, you always have to add free sulfate in this fit. Okay, but you also have to manage if the sulfate are bidentate or monodentate, and from this data, it is not easy to determine whether it is one way or the other. And this is why we wanted to complement this work with some modeling. And I have a colleague here at the ICSM, Magali Duvay, who is doing molecular dynamics models with force field that are adapted to do organic solution, and where she were able to make this calculation. Okay, and the result is exactly the same as what we have shown from the EXAFS experiment. We have free sulfate anion, and in some cases, 3 are bidentate, and in some other cases, 2 are bidentate and 1 is monodentate. You can also, what you can't do with EXAFS, you can do it with molecular dynamics, is that you can track the configuration over time. And in the molecular dynamic time scale, you have, you can, by measuring the uranium sulfur atom distance, you can look at when you have one configuration or the other. When you have 3 bidentate sulfates, you have the 3 uranium sulfur atom distances that are the same. And then sometimes when it becomes here in the blue area, it splits and you have the second configuration, and then it comes back and again like that. Okay, the last thing you can do from this molecular dynamic calculation is you can just take some snapshot of the trajectory of uranyl, and then you can make an exact spectra out of it. And this is what Magali did, and we can select either the blue part or the red part or the total calculation to make exact spectra. And as you can see, it works quite well, and you can compare it to the actual experimental data. So it closely reproduces the exact spectrum. You can see that the free bidentate sulfate looks to be better than the other. And this is a fine tuning of the molecular dynamic model. So now the thing is going back to the model people who can tune their model to reproduce better the experimental data. So now I directly jump to the other end of the nuclear fuel cycle, where you have to separate uranium and plutonium, and we use in France the Purex process, which is based on solvent extraction of uranium and plutonium, and then a separation of uranium and plutonium by reducing plutonium to the plutonium-free oxidation state. And we develop other alternative solvent extraction process that are based on other molecules, and more particularly the amide function-based molecules, which is kind of a huge family that you can also tune to change the extraction properties. The only other difference is that instead of using this difficult redox process to strip the plutonium from the organic phase, in this case, you do not have to deal with this plutonium redox reaction. You have to only deal with the acidity of your aqueous solution. How does this work? Okay, we can use this sketch to understand, and then I will go to spectroscopy to explain why what we do is useful to understand that. Is that you can measure a distribution ratio. It's the ratio between organic concentration and aqueous concentration of a metal over the acidity of the aqueous phase. And you see that the more you have an acidic solution, the more you are going to extract plutonium, for instance. Here, that's the red points. And you also can measure the separation factor between uranium and plutonium just by doing the ratio of the distribution ratio. That's the green points that are here. Okay, so the process works this way. You first go to high acidity where you have good distribution ratio for both elements, and then you go down to this position where the plutonium is less extracted, and then it will go down to the aqueous solution. So what we want to understand here is what is the role, what happens if you change the design of these molecules on this distribution ratio coefficient, and what happens also while you are changing the acidity in the aqueous phase for the plutonium structure in the organic solution. Fine. So the first step is to try to get an idea of what is going on if you change the structure of the extracting molecule. Here you have two examples. This is exactly the same molecule. Only one is linear. The other one is a branch monoamide function. And you see that the extraction property drops down drastically. So it's just this thing change everything in the extraction property. And we wanted to understand what is going on in the organic phase. If you do an exact spectra of it, you are going to find almost the same exact spectra. So it seems that you are extracting the same complex in the organic solution. And if you want to fit it, we have XRD model of tetranitrate compounds with two extracting molecules in the first plutonium coordination sphere that works pretty well to fit the linear alkyl chain system. If you go to the branch alkyl chain system, you are going to fit it also, but you have kind of changing values compared to the XRD model that seems to be not completely perfect. Okay, and I will come back to that a bit later. Now, the second aspect I wanted to look at is that if you rise the acidity in the aqueous phase, okay, you are changing the extraction properties, and we keep the same extracting molecule here. And here is what you measure. You are measuring, okay, the same spectra for the lower acidity, and then by rising the acidity, you are going to be in trouble if you want to fit the data still with this tetranitrato inner sphere complex. Okay, so what we need now from that is we need another structural model to fit our EXAFS data, and this is where the calculation will come to our help. Okay, if you want to model an EXAFS signal, what we usually do is we use FEF, and also we sometimes use DFT optimized geometry to get an idea of distances and different scattering path lengths that you can use to do a fit. What we also did in this study is that we used this DMDW module of FEF9 to extract from DFT vibrational frequency some ab initio de Weller factor that we can also include to fully ab initio model an EXAFS spectra for different complex structures. And we used it for, okay, still the same tetranitrato complex. We tried something with, instead of 2 ligands, we have 3 ligands. We also tried with 6 nitrate and the ligand in the outer sphere, or 5 nitrate and 1 ligand in the inner sphere and 1 ligand in the outer sphere. And with that, we have kind of a library of EXAFS spectra for different structure that we can compare to our signal that we measured in the synchrotron. So let me go back now to the effect of acidity. We have these 2 models that works pretty well. One is working quite well if you compare the simulated spectra, which is the open circles here, to the experimental data that we measured at lower acidic condition. And if we compare what we obtained for the higher acidic condition, now we have a model which is the outer sphere complex with 6 nitrate ligand that works pretty well. Okay, and out of that, I'm just doing a step aside because we have also labs and we have tools in the labs. Out of that, we can use this information that we had from EXAFS and DFT now to daily track the speciation of plutonium in organic solution using visible spectroscopy. So this is one use of molecular structural analysis that we can do that is directly transferred to application in our lab. Now I'm coming back to this difference between the 2 monoamide structure, and I compare again to our DFT model spectra. So as I said, the tetranitrate inner sphere complex works pretty well for this one. So this we knew already from the fit, but it confirms that the DFT approach to model an EXAFS spectra in this case works pretty well. And if you try other structures, it works much less. And now if you look at the branched alkyl chain monoamide, what you will observe is that over all the spectra we tried, we have 2 kind of positive response from this data, is that if you mix up, in fact, this inner shell with this outer shell complexes, it works pretty well too. Or if you are going to work with a pentanitrate system, which is in terms of EXAFS, is overall equivalent. Okay, so as I said, the best model is inner sphere complex for this one, and for low acidity, the best model for this one is a mix of inner sphere and outer sphere. And the outcome of this thing is that we have a better understanding of what is doing the alkyl chain on the plutonium speciation and the organic phase. In fact, bulky ligands around the branch alkyl chain will favor outer sphere interaction against the inner sphere interaction that you will form if you have only a linear alkyl chain. So with that, I can summarize. We have both experimental and theoretical studies to investigate plutonium-6 and plutonium-4. Molecular dynamics helps to get an appropriate uranyl sulfate system optimized and understand it. And now we can go further using molecular dynamics to understand how this interacts with the organic phase. DFT works well also in organic phase. It is something that you have to check by comparison with XRD model, because there is other systems where it doesn't work. And there is several outcomes for industrial processes, like for the Amex process, we know now the stoichiometry of the complex. We are trying to look at some modifier they add in the industrial case. And we have a better description of what is going on with the amide type extraction system. With that, I thank the people who participate to this work here in Marcoule in my group, the colleague at the ICSM, and the people who helped to do this measurement on synchrotrons.
Thank you very much, Thomas.
Thank you.
Excellent talk. Thanks a lot. Really nice example how in fact theoretical simulations and all this kind of geometry optimization can help even in the data analysis, right? For access. I have a question for the geometry optimization. Which program or the software do you use? Or did you that time?
So it's Dominique Guillaumont with the office next to mine. It is using Gaussian mostly for this thing. Yeah, and if you want some details about this part, I have here noted the publication where you get more methodological information if you need.
Excellent. Yeah, exactly. So it's just published in Inorganic Chemistry. Yeah. So I believe for the DFT you also use Gaussian for the DFT.
Gaussian, yes. Yeah. I guess, yeah, I don't think she uses anymore ADF, but it's, yeah, it's mostly Gaussian.
Okay, excellent. Tama, thank you very much. I guess we are perfectly in time. We stop now for the coffee break.
Okay, first of all, I would like to thank the organizers for giving me, I have to see myself as well. For giving me the opportunity to present our results and the invitation to give the presentation. And here is what is happening. And here is the outline of my talk. So first, I briefly discuss the concept of high energy resolution fluorescence detected X-ray absorption technique, in short HERFT SAS, at Actinide images, which this technique actually takes the advantage of photocore RIGS 3 to 4F, actually resonant inelastic X-ray scattering, or the other name for that is resonant X-ray emission. Then I will present the results of the calculations of the HERFT spectra and the 3D 4F RIGS maps for a series of actinide dioxides. Then I'll compare the results of the calculations with the experiment. And in the end, if I have time, I will talk about the dependence of the HERFT spectra on actinide coordination number. So this slide shows the schematic representation of the HERFT process for actinide using 3D to 4F transitions. So if we tune the energy of the incident photons to the 3D threshold, the system, by absorbing of the photon, can be excited into the high energetic states with the 3D hole. And this step is actually corresponds to doing X-ray absorption spectroscopy. So by scanning the incident energy and counting all the photons outgoing from the samples or electrons, regardless of their energy, we will measure conventional X-ray absorption spectrum, which will be broadened by the 3D co-hole lifetime. But these co-excited states can decay into states with 4F co-hole. And if we have an X-ray emission spectrometer, so we can tune it to the energy of the 3D to 4F transition. Usually it's done by tuning it to the maximum of the emission line. And then count only the photons of this energy while scanning the energy of the incident photons. Then we'll record a spectrum which will be broadened by 4F co-hole lifetime. And the difference in co-hole lifetime broadening is actually quite large. So the 4F co-hole lifetime broadening is 4 to 8 times smaller than 3D co-hole lifetime broadening, according to different estimates. That should improve the resolution of our spectra. And indeed, so the slide shows a comparison of the Hertz spectra with conventional XAS spectra at actinide M4H for thorium dioxide and uranyl nitrate. So, and you can see a dramatic improvement in resolution here. So we are able to resolve additional structures, even small satellites here, instead of a single line for thorium dioxide. And instead of a hint for a shoulder here for uranyl nitrate, we resolve like 4 different structures. So of course, the right way to do it actually is to measure the whole map, 3D 4F RIX map, as it's shown here, like intensity map around the M beta line in UO2, so which is shown on the incident energy axis and the energy transfer axis. So then one can make a cut, diagonal cut through the maximum of the intensity here, and then obtain the Hertz spectrum. One can actually make different cuts and obtain different information in this case. And here we see the improvement in the Hertz spectrum compared to conventional SANES. But you should realize here that the whole effect of this sharpening, it comes from the 3D 4F RIX contribution here. Of course, this way to do measurements not always suitable, because it's time consuming. It's not possible to do it for dilute or fast degrading under the beam systems. And also, if you make a cut, usually it's much more noisier compared to direct measurements of 1 Hertz scan. But I mean, like using, for example, 1 Hamer's spectrometer can help in these problems. So the more and more researchers now started to use this technique because of the enhanced resolution, improved resolution and enhanced sensitivity. But that raises some questions. How well do the profiles of the RIX spectra at actinide images follow the X-ray absorption cross-section? And can the Hertz spectra be actually used to characterize the chemical state of actinides or distinguish between various species? So I'll try to address these questions by doing crystal field calculations to start with of the 3D 4F RIX maps, conventional XAS and Hertz spectra. And unfortunately, I have to skip the details of the calculations, but they are actually published in this paper already. So one can take a look there if interested. So here, this slide presents the results of these calculations. Panels A show the RIX map on the incident energy axis and the energy transfer axis. And you can see there are two groups of transitions here, which are related to 7/2 and 5/2 of the 4F 13/5F n+1 multiplet. So on this energy separation is actually governed by the 4F spin orbit interaction, and it increases when we go, this energy separation increases when we go from thorium to californium. Panels B show the same map, but on the incident energy axis and emitted energy axis. And panel C show a comparison between the Hertz spectra and the conventional excess spectra, which are actually with reduced broadening for comparison. So there are systematic differences, as you can see, between Hertz spectra and X-ray absorption spectra at these M5 edges of actinides. So one of them is the lack of intensity on the low energy side of the Hertz spectra, which are in red. And then another one, appearance of additional transitions on the high energy side of the Hertz spectrum. Here, it's even more pronounced for plutonium, americium, and curium. So you can see here. But these differences, especially the lack of intensity on the low energy side, can be understood in terms of considerations which were described initially by Tolle and van der Laan for L edges of 3D systems. So in our case, the high spin states of the 3D 9 5F n+1 multiplet will tend to group on the high energy side, on the low energy side here, while the low spin state will tend to group on the high energy side here. And then we know that high spin states actually tend to scatter elastically or to the states with low energy transfer, while low spin states tend to scatter inelastically. So then in the case of high spin state scattering, they will have reduced inelastic scattering weight, which we observe actually here. The differences on the high energy side of the Hertz spectra is easy to understand by looking at the example of thorium dioxide. So for thorium dioxide, the 3D9 5F1 multiplet, has the highest state at the energy of this strong peak. So there are no other states of this multiplet, while we still see some structure in the Hertz spectrum of thorium dioxide here. So to understand why it appears, so you should look at the RIX spectra actually taken at these incident energies A and B. We can see that for the emitted energy of the Hertz cut through the maximum of the RIX intensity on the RIGS map, we still see that the spectrum B has some contributing with some intensity. And this spectrum is actually consists of transitions to the 4F13 5F1 multiplet. So, and this multiplet has a larger energy spread due to larger values of Slater integrals. So it means that the appearance of this high energy structure actually is the final state effect of the 3D 4F RIGS process. The calculations actually show quite a large difference for the californium dioxide between the Hertz spectrum and the excess spectrum for M5H. Anyway, despite all these differences between Hertz and excess spectra, one still can use this Hertz technique as for studying of changes in the chemical state, because for most of dioxides, the maxima of the Hertz and the excess spectra coincide, actually. So then one could use shifts of that to judge on the changes of the chemical state, for example, due to covalency. The RIGS maps for the M4H actually calculated are quite different from those at the M5 edges. In particular, here you can see two groups of transitions here and here, which are quite a few eV below of the main structures and above. And these are, again, the final state effect due to 4F, 5F exchange interactions. So it's very easy. You just switch off these integrals in calculations and these structures disappear. As to difference between Hertz spectra and Xas spectra at the M4H, we can see that the Hertz spectra actually reproduce all the structures of the Xas spectra, but the relative intensity can be different. For example, here for uranium dioxide or for neptunium dioxide. The only large difference is found for americium actually here. Otherwise, they are okay. So it seems like overall agreement between Xas spectra and Hertz spectra is better for M edges. So I would recommend to use those edges in your studies. Okay, now is a to comparison between experiment and the calculations. So I actually was quite surprised to see such a good agreement, because it's only crystal field calculations without taking into account hybridization effects. But you can see quite a good agreement here, here, and here. For thorium dioxide, these small satellites are not reproduced because, of course, one needs to take into account, besides 5F oxygen 2p hybridization, also in 6D states as well. Those are important for this system. Actually, starting from plutonium dioxide up to californium dioxide, the charge transfer effects or hybridization effects of the 5F states with the oxygen 2p states become important. Therefore, here the experimental data are compared already with the simplified Anderson impurity model calculations, where the hybridization dependence of the hybridization function on energy is actually neglected. So this improves agreement between calculations and experiment, and tells us that, yeah, this should be included in calculations. This slide show a comparison of Anderson impurity model calculations results like Riggs map and Hertz spectra for two compounds, uranium dioxide and the uranyl nitrate. Uranium dioxide, of course, the charge transfer effects and the hybridization effects, they are not that really strong here. It was, yeah, just used as an example as a model system. So the Hertz spectrum is not very different from the calculations using only crystal field multiplet, because the charge transfer energy in this system is quite large. But what I would like to point out here that you can see in the experimental data that there are these weak transitions which correspond to transitions here calculated due to 4F, 5F interaction in the final state. So this is the final state effect here. And the other counterpart is not here because the range, the region measured here is, it goes like this, I think, if I remember correctly. So that it's, these transitions are on the boundary to be detected. So we need another experiment to check that. For uranyl nitrate, actually, the charge transfer effects and the hybridization, it's become vital, actually. So that one has to take that into account. And yeah, the Anderson impurity model sort of reproduced these satellites, but of course they lack intensity, so more sophisticated calculations I think needed. But the comparison of the Riggs maps are not so bad. I actually forgot to mention these tails, which are actually corresponding to the characteristic emission, which is of course not included in the calculations. Yeah, so yeah, now I'm moved to the dependence on of this Hertz spectrum on actinide coordination number. It's actually a question how sensitive this Hertz spectra can be to changing in the actinide coordination number. But it's not easy to study this point experimentally because between different compounds, there is a difference not only in the coordination number, actinide coordination number, but also on the actinide ligand distance and charge on the ligand. So, but it's easy to do it in calculations. So using the point charge electrostatic model, I just set the distance to be the same and the charge to be the same for different polyhedra. And then it's easy to find the relation between crystal field parameters between different polyhedra. Then, so as it's shown here, the crystal field parameters for tetrahedron, octahedron, and the cube octahedron, which are related to the crystal field parameters for cube. And these are basically one can take like crystal field parameters for your uranium dioxide and then calculate for other polyhedra. So, and that's what I did. And the spectra are shown here. You can see that, indeed, there is a dependence entirely on the coordination number, but there is no trend. So we go from CN4 down to CN6 and then back to CN4, and then a little bit higher the intensity of this shoulder for CN12. And if when I did the calculations for another ion, uranium ion, but 3+, then the behavior was very different. So unfortunately, one can't actually establish any trend in the dependence on the coordination number, but the spectra do change. Okay, so I came to summary, and then I would say that yes, indeed, the HERF technique can be used actually for studying the chemical state and the speciation, despite some differences which are found between HERF and the conventional XAS spectra, because the gain in the resolution and in the sensitivity is so dramatic, so that one can maybe not neglect these differences, but in some cases to do actual calculations to interpret the data correctly. And in the end, I would like to acknowledge my coworkers who helped in getting the experimental data or who provided with nice samples. In particular, the top group, which is led by Kristina Kvashnina. Thank you for your attention.
Okay, thank you very much, Sergey. I think there is a question maybe from Hao Cheng. How? Yes. Do you hear me? Yes, okay, you can ask your question live.
Yeah, very nice talk. I like it very much. I learned a lot. I have a few questions. One is when you do the simulation to show that the absorption is different from the how do you call it, Hertz spectra?
Yes.
Did you use the same lifetime for the XAS as for the Hertz? In the simulation, because in the experiment one is 4 times bigger.
No, but the lifetime actually affects the broadening of the spectra. So I used the same lifetime as for the final state of the Hertz. So it's like, as I said, reduced broadening for X-ray absorption spectrum. So in reality, the real X-ray absorption spectrum will be much broader. So, but then you can't compare with Hertz.
No, I understand. Okay, so
the idea was to see the comparison, actual comparison. So, but in reality, in real life, you are not able to do that.
No, so now I understand. Of course, I understand your point. So you want to simply show that principally the X absorption is different from Hertz, right?
Yes.
The next question I have is very quickly. You have done this calculation in ionic manner, right? And then later you do this Anderson impurity in which you include hybridization. You must have also have changed the so-called Slater integral reduction. Is that correct?
No.
You use the same Slater integrals?
Yes, exactly.
Why then it does not be sensitive?
Because reduction of Slater integrals, yeah, maybe affected, but not that much due to hybridization. It's the main effect comes from the configuration interaction for atoms themselves.
For the atoms, I see.
So that I mean, in reality, when you do calculations for atoms, you have to include numerous number of configurations, and it's not possible.
No, that I understand that already on atomic level.
But hybridization do affect to some extent.
Because we work sometimes with highly covalent system, and then if you do an ionic calculation for a highly covalent system, then you have to reduce quite a bit.
But say like uranium nitride, uranyl nitride, sorry. So it's a highly covalent system. And, but there, the reduction of Slater integrals may be by 10% more. I mean, you would need, not more. I mean, or I mean, there are some model parameters which you have to use, and that already, I mean, brings some uncertainty. So you want to minimize uncertainties by changing lots of parameters. So you don't want to do that. So that you
okay.
try
one final question.
If you get good results, then you're, I mean, you're happy.
Okay, good. So then one last question. This is what the chemistry part. Why is it, if you go to the later actinides, that the hybridization with the oxygen is more important? I would expect the opposite. The more you go to the right, the smaller the 5f orbital will be, so that then the hopping integral will be less.
This is confirmed actually by other spectroscopic means, for example, from photoemission calculation of spectra photoemission and other techniques so I just agreed with that.
I see.
In a way, because the calculation reproduced the experimental data for other techniques as well. So then,
yeah, I don't question that. I simply want to know the why in terms of chemistry.
Then, for example, like if you do photoemission calculations, then you end up with the 5f occupancy numbers, for example, and then it's clear they increase when you proceed to Californium and stuff like that.
All right, thank you.
Yeah.
I have two other questions from the audience. The first question is from Michelangelo. First of all, he said, great talk, and I agree, it's a really great talk which you have given. What you have shown are isotropic spectra, is that correct?
Sorry, once more.
The spectra which you have shown are isotropic spectra.
For X-ray absorption, yes, but not for X or HERFT. There I took into account, and you have to actually take into account the experimental geometry, because the spectra may change depending on the geometry. It's actually also one of the advantages of the technique. So then you could actually change the geometry and see what happens, and then, I mean, probe different states in a way. So that's, I think, yeah, an advantage. But it's compared with isotropic X-ray absorption spectra, although in the paper I am saying that I also calculated for the same geometry, the X-ray absorption spectra, but they don't change very much.
The last question for Michelangelo is, are all your parameters ab initio, or do you have fitting ones? Do you screen the monopole for 4F, 5F exchange interaction?
Monopole? Sorry, I have a call. Yeah.
Okay, so. I mean, if you
no,
can...
I have not screened the exchange interaction. No, that one thing. Yeah, and it may be a reason that, for example, the high energy part does not appear in the experimental spectra, but I mean, we have to measure that. Anyway, that is one thing. And what was the first part of the question?
Do you have, are all your parameters ab initio, or do you have fitting ones? Yes.
Do I have what? All
fitting ones.
No. Yeah, the beginning of the question once more. Can you read? Can you read once more?
Are all your parameters ab initio, or do you have a fitting ones?
Ah, okay. So that the Slater integrals are ab initio. They are calculated using the Hartree-Fock method with relativistic corrections. So, but then of course they scale down to 80% usually of the ab initio value, because this is a consensus usually in the spectroscopy community and stuff like that. So that's what you do. And they are ab initio, yes. The crystal field parameters, they were chosen based on literature research. So of course one can calculate crystal field parameters, for example. It's not that actually easy, but yeah, I mean, with the DFT techniques. But yeah, I did not bother to do that. It's a lot of work. I just used recognized values for I mean, which were approved by different techniques and stuff like that. So that makes your life easier. As to Anderson impurity model calculations, these are parametric calculations, but of course, again, there, I mean, it's only for a couple, three cases, but there, what you do, you can also use DFT constraint techniques to calculate some of them, not all, unfortunately, but some of them. But also the other way is, again, to use more or less recognized values, or I mean, which were derived from different techniques, or confirmed by different techniques as well. So.
Okay. Thank you, Sergey. Again, thank you very much for your very impressive talk.
Fabrice, can I ask the last question?
Yes, you can. Yes.
Can I? Sergey, can you go back to your slide when you show uranium M4 calculations for UO2 and for uranyl? Exactly. No. Yes, this one exactly. So I'm curious about this low energy part, which is 5 eV below the main excitation. You do have it exactly in UO2, but according to calculation, uranyl doesn't have it.
No, it doesn't.
So it means it will depend on the number of 5F states.
Yeah, I mean, you can see here. So if I go here as well for thorium dioxide, you don't have it. So it starts from uranium. I did not calculate for 5F1 configuration actually, so I don't know if it appears there, but probably it will appear there. So it's just F0 configuration in the ground state, doesn't lead to that.
Yeah, so that was my next question. If you know how 5F1 will look like. You didn't calculate 5F1.
No, I didn't calculate 5F.
Okay, thanks.
Because there are no data to compare. So, I mean, it's additional work. One has to always compromise.
No, didn't we measure uranate with sodium UO3? I think we did, no?
Yeah, exactly. So, but
so we should look in the RICS.
Was to use a unified approach. So it's like a crystal field approach. If you go to highly covalent systems like U5, U6, so you need to use Anderson impurity model, and then you have to use parameters or whatever, or calculate, but not all. Parameter values, and then you introduce additional uncertainties, and that's what I did not want to have to start with, because I wanted to compare things. But like a single spectrum for some system or something, of course, one can do these kind of calculations and see.
Yeah.
Okay, I think we have to go ahead with the next talk.
Excellent talk and excellent paper.
Okay, thank you again, Sergey.
Yeah, okay.
Okay. So the next talk will be given by Alexander Schick from the Institute of Physics from the Czech Republic. And the title of his talk will be Correlated Quasi-Particle Dispersion and ARPE Spectra in the newly discovered uranium telluride, ditelluride.
What should I do? Share the screen?
Share the screen.
And then go to the presenter mode, right?
Yes, yes. And then you have to select the PowerPoint window.
Okay. Can you see me?
I see you, but not your presentation yet.
Not yet. Okay. Share. Okay. You see it?
Yeah, yeah. The first slide is superconductivity.
Jerry, let me just sort of tell you the motivation. If you look at the superconductivity periodical table, or we call it Tablica Mendeleeva, where I mark the elemental solids which are superconducting. If you examine the table, you realize that those materials which are superconducting usually do not have a magnetic order, like traditional metals like iron, cobalt, nickel, or rare earths, or most of the uranium, most of the actinides. They cannot be superconducting. They are not in blue. So perhaps there is a problem of coexistence between the superconductivity and say ferromagnetism. And actually this issue was around for a very long time. So coming back to the very early days of the superconductivity, we all know about the famous Meissner effect. If you take the magnet and try to put on the superconductor, it will just flow up. It is known as a levitation, magnetic levitation. And the origin is that actually the superconducting material expels the external magnetic field which is applied. And then early on in like 60s, famous Russian theoretician Vitaly Ginzburg asked the question, what happens if the ferromagnet would become a superconductor? The first thing is that you immediately realize that if you have a ferromagnet and you assume it in the superconducting state, you will get the surface circulating current which will shield the magnetic field coming out of the superconductor. He called it inverse Meissner effect. And then he also made some estimates. Since that time was already known that if you consider the phase diagram of the superconductor, here's the temperature, here is the field. If you are in the superconducting phase and apply the field, at some point, which is called critical field, HC, superconductivity disappears. Indeed, you can think of the internal field due to the magnetic dipoles inside of the ferromagnetically ordered solid, and he did some simple estimates which gave him the fields in the range of kilogauss to 100 kilogauss. And that time it was already known that, that the critical fields are about 10 to kilogauss. So the critical field is less than internal field due to the magnetization. So the conclusion was the superconductivity just cannot survive the internal field due to the magnetic moments in the ferromagnets. Well, indeed, one comment I want to say that this time in 1957, so-called type 2 superconductors were not known because there are two critical fields. One is the lower critical field, another is upper critical field. As soon as the magnetic field can go inside of the superconductor and create somewhat mixed phase with parts of the superconductor which are in the normal state and parts are in the superconducting state. But he was considering only type 1 superconductors. Okay. Doesn't okay, no. If you think of, indeed, since then there are a lot of developments in the theory of the superconductivity, and usually we deal with what is called conventional superconductivity, where the pairing, superconducting pairing, is due to the electron-phonon interaction. If you think of a conventional superconductor where there are two electrons with spin up and spin down, and they form the Cooper pair, due to the attractive interaction, due to the phonons, then you can think about the superconducting pair wave function due to the Pauli principle as being antisymmetric. Indeed, since the spins are different, the spin part of the wave function is a singlet. And then, if you can imagine what happens when you apply the field to this singlet, then the Fermi surfaces which were the same for up and down before the field become different, so they shift. And if this shift is eventually less than superconducting TC, which measures the strength of the pairing interaction, then the superconductivity can survive it. But usually this shift is more than superconducting TC. It means that the conventional superconductivity is usually destroyed by the magnetic order. Well, but on the other hand, the spin part of the Cooper pair doesn't have to be antisymmetric. It could be symmetric. And in this case, we have what is called triplet superconductivity. Then the spatial part indeed should be odd. So in principle, it was a purely theoretical proposal for many years until the first ferromagnetic superconductor was discovered, and it is uranium germanium 2. So it was discovered, if I am not mistaken, around year 2000, so already 20 years ago. And since then, there were more developments, and more materials came around, like uranium rhodium germanium, uranium cobalt germanium, and finally, about a couple of years ago, it was discovered uranium tellurium 2 as an unconventional superconductor. And our American colleagues eventually created some kind of cartoon saying that if you go from uranium germanium 2, which is a ferromagnet, and becomes superconducting under the 12 kilobar pressure, you go to the left-hand side, you destroy the magnetic ordering, but there are still spin fluctuations which mediate the superconductivity in uranium tellurium 2. Well, I want to look at the endpoints, this one and that one. I'm not going to talk about those two materials. Let me first remind you, or just introduce uranium germanium 2, which has an orthorhombic structure. It orders ferromagnetically at 52 Ks. And if you look at the phase diagram, here you have first transition to the ferromagnetism to so-called FM1 phase. If you don't apply the field, this phase has actually low moment around 1 MeV. Then you cool it down, and then you cross into the what is called FM2 phase, which has a higher moment, about 50% higher. So, and then once you apply the pressure, you end up in this superconducting dome, which is eventually corresponds to this critical point, where the FM1 meets the FM2. So indeed, there were a lot of measurements by neutron scattering, magnetization, what anything people had in hands. But the problem is that you cannot measure the magnetization inside of the superconductor due to the fact that, as I said, this inverse Meissner effect doesn't let the magnetization out of the superconductor. So you cannot just place it into the magnetometer and you will see nothing. So you can either use the muons, but this is very special probe, which doesn't give you exactly the quantitative description of the local magnetic properties. And XMCD is eventually the actually the perfect tool to go inside, because the X-rays can go in and you can measure the XMCD. Roberto in the morning already mentioned what is XMCD. I will probably not repeat. And you can measure not only the spin and orbital moments, not only the spin moment, but also the ratio of the orbital to the spin moment using the sum rules. And that's actually what was done in USRF by Fabrice and collaborators. And here is the result. This RLS ratio versus pressure. And you see that not only the total magnetization changes when you go from FM2 to FM1, but also the ratio is changing. It is getting smaller. So then, indeed, you wanted to check whether it comes out in the calculations. And first thing we did the calculation of uranium germanium-2 using LDA plus U. Eventually, we obtained two solutions: FM1 with the lower moment and FM2 with the higher moment. And actually, if you look at the energy dependence on the volume, you see that near the equilibrium, they are practically degenerate. So you don't need much of the energy to move from one state to another state. And then when we look at the properties of these solutions, like spin moment, orbital moment, and the ratio, we see that at zero pressure, our ratio is close to the experimental value. Then we increase the pressure. Again, if we are in FM2 phase, we are close to the experimental value for FM2. But then, if we increase the pressure, we can reproduce the RLS ratio according to the experimental data. So it decreases. So moreover, we also look at the total moment, which corresponds rather well for the high moment phase and for the low moment phase. So here the deviation is somewhat bigger, but we don't know why. So, but the RLS ratios are in the good agreement with those XMCD measurements. Okay, we wanted to look into the microscopic reason for that. And for this reason, I plot the densities of states of F projected densities of states on the uranium atom. And I resolve them into J equal 5½ and MJ, this is a projection on the easy magnetization axis. So these are 5½ in red and 7½ in blue. Then if I compare those for FM2 states at zero pressure, I see there is a change for this -1½ +1½ states in FM2 and FM1 phase. And actually this change becomes even more pronounced when I go to the FM1 state under the pressure. So in the sense that those electrons which were sort of shared between those states now jump into the state with MJ 1/2. And we call it orbital differentiation between those two phases. So in a sense that when you apply the pressure to uranium germanium-2, you sort of change the occupation of the, not the total occupation of the F shell, but the electrons are redistributing between the different orbitals on the uranium atom. So, and I will make some kind of intermediate conclusions saying that our DFT plus U calculations agree rather well to the experimental observation showing the change in the RLS ratio when you go from high moment to the low moment state of uranium germanium-2, and we found the reason for that as an orbital differentiation between those two phases. At this point, I want to acknowledge the collaboration with my colleagues from the ESRF. And the next material I want to talk about is uranium tellurium-2. So this guy is also orthorhombic. It is superconducting below 1.6 kelvins. The reason why it became so popular, and there at some point were many papers in the top journals about this material, because when they measured the specific heat versus the temperature, they thought that this specific heat doesn't go to zero as usually in the superconductors. It eventually means that only part of the electrons are in the superconducting state, while other part is not in the superconducting state. And actually they show it like here. You see, this is like 50%. Well, later on, it turned out that just they didn't cool down low enough, because at the end, there is this race, but then the specific heat goes to zero. So this initial excitement eventually was not really so well justified, but anyway, it's an interesting material. And people started to investigate the magnetic properties. It is a paramagnet, but it has very strong anisotropic magnetic susceptibility. You see, it is shown here. Along A, it is much higher than along B and C axis. At the higher temperatures, they estimated the magnetic moment around 3 MeV, and they were, especially due to this unusual behavior of the specific heat, there were many proposals that it is a half-depth unconventional superconductor. It seemed to me a little bit meaningless these days, when it is clear that there is no really this phenomenon. So, and the first thing to do indeed is to look at the electronic structure. And when we do the conventional density functional theory, we did it, some other people did it, and everything is coming to the end that and indeed it includes the spin orbit coupling, everything. So that the material is actually semiconducting with the small semiconductor gap of, like I wrote here 13, but different calculations differ like from 10 to 15 millivolts. Then the question is, how come it has a high gamma of 120 millijoules per Kelvin squared per mole? How the semiconductor can give such a high gamma? Moreover, how can it become superconducting? It means perfectly conducting. Therefore, one clearly needs to go beyond of conventional density functional theory to deal with this issue. And since the material is not magnetically ordered, you have to go, you cannot really straightforwardly use the methods like LDA or DFT plus U, because they tend to work only for magnetically ordered phase, the purely Hartley-Fock-like calculations. So you have to go beyond of the Hartley-Fock. And that's what we did. And we took moderate U, which is kind of common for uranium. We took 3 volts, while we could take 2.5 or 3.5. We didn't really calculate it ab initio. So this is the usual believable value of the Coulomb interaction on uranium. And J is ½ volt, which is also a conventional number. And then we got it semi-metallic. So this gap is closed. If you look, let me say maybe a couple of words about our method. The difference between the conventional LDA plus U and our extension, that we do not calculate the occupation matrix inside of the DFT plus U, which would correspond to the single determinant approximation. Instead, we obtain the parameters from DFT or LDA plus U and solve Anderson impurity model with these parameters and calculate there the occupation matrix. And then we put it back to the LDA plus U, and we do it self-consistently. And indeed, we include the spin orbit coupling, we include the crystal field, we include the full interacting matrix, and we use accurate full potential LEPW method. So let me show how our, let me go to the experimental results. There is some controversy in experimental data regarding the photoemission. So here is angular integrated photoemission by Fujimori from Japan and by Miao from the United States. One is taken as at 4D5F edge and corresponds to the photon energy of 800 volts. Another is taken at 5D5F edge and corresponds to 100 volts. And you see the difference is actually huge in the sense that there is no peak near the Fermi in those Miao measurements, while there is this peak in the measurements of Fujimori. Obviously, if you do these kind of experiments, you are surface sensitive because it's just this photon energy is just too low to avoid the substantial surface contribution, while these photoemissions seem to be less surface sensitive. So if you do the comparison with the measurements of Fujimori, here is my density of states. Here, these are F states, and these are the P states. I just blow them just to see, to be seen better. And this green line is the experimental data. Well, in fact, the comparison is rather good. So in a sense, our calculations support the Fujimori's measurements and are in disagreement with Miao measurements. And if I just blow up my density of states near the Fermi edge, I see that exactly the Fermi, the density of states is not so high, but then 10 millivolts above the Fermi, there is substantial peak, which gives me the gamma of 70 millijoules per Kelvin square per mole, which is already reasonably close to the experimental value. Well, these are just band structure calculations. It means there is no dynamical enhancement or mass enhancement of the gamma, and there are no phonons. Therefore, this is already not really unusual difference. So next thing we did, we made a comparison with the experimental angular resolved photoemission. Here are the Fujimori results, here, 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 and here are our calculations. You see that near the Fermi edge, the bands really fit very well to what they measure. Here, here, and here. So if you look at the Fermi surface, because it's a semi-metal, with very narrow flat F-bands near the Fermi edge, the Fermi surfaces look like this with some small pieces of the holes and the electrons. And altogether, they indeed compensate each other. If you look at the densities of states from each of those pieces, you see that most of the density of states is an F electron density of states. Moreover, we can calculate the Fermi velocity, and we see that there is a pronounced anisotropy in the Fermi velocity. And if you take the ratio of the Fermi velocity, say, along the A direction and the C direction, it is about 1.44. Well, naively, you can say if the electron moves faster, then the material conducts better. It means that this ratio, at least qualitatively, is inverse proportional to the ratio of the resistivity. And actually, experimental ratio is about 2. All right, so then I come to the conclusions. The first thing is that uranium atom and uranium tellurium-2 seem to be close to the F3 state and not F2 state as it was proposed from the measurements of the Miao and corresponding theoretical analysis. And when you consider the correlations, then your band structure turns from the narrow band semiconductor to the flat band semi-metal. And our calculations provide actually good quantitative agreement with both angular integrated and angular resolved photoemission. At this point, I would like to acknowledge my collaborators Warren Pickett from UC Davis and Shinichi Fujimori from Japanese Atomic Energy Agency. And the last thing I would like to say that indeed any X-ray XAS like XMCD or more sophisticated techniques would be very welcome to quantify the F electron character in this material. I'm not aware, except of some X-ray absorption measurements by Fujimori, who also provided who also suggested the F3 configuration for uranium in uranium tellurium-2. I didn't see anything which was done so far, and I hope in years they can make new measurements. Thank you.
Thank you very much, Sasha, for this very nice talk. So I hope that indeed in the future we will work a little bit on this uranium detelluride. And I guess certainly it will be possible to do ZANES measurement as well as XMCD on the very high field. Does somebody have a question to Sasha? I look a little bit on the question answer box. I do not see one. I have a question regarding this orbital differentiation, which you talk about for uranium germanium 2.
Okay.
Does it mean that the number of 5F electron does not evolve as a function of the pressure, or when you go from this FM2 to FM1
no.
ferromagnetic state?
No,
is it constant?
It is not exactly the constant. It is varying a little bit, but somewhere in hundreds.
Mm.
So there is no any noticeable change like you would expect in metal insulator transition. Because some people were saying that when you apply the pressure, you go from the localized to the itinerant state. That's not what happens. This pressure is still not big enough to induce such an effect.
Okay, because it is also said that under pressure you may change a lot the hybridization, and then we'll also get, and this will may also give rise to.
Actually, I can actually show you this thing. I was afraid that I will have not really much time to talk about all the details. I prepared some. Here are the hybridization functions in the FM2 at 0 pressure and at FM1 at 20 kilobars. This hybridization function is a function of the energy, measures the strength of the hybridization. There is not much change. They are not really equal, this to that, but there is no any drastic change in them.
Okay. Another question related to uranium tellur-2. Have you tried to calculate this when you apply, or in calculation you can, let us say, simulate a magnetic field, external magnetic field? Because you
not yet. No. Those calculations which I was showing for uranium tellurium-2 were without the field.
Okay. If somebody else has another question,
yeah,
let me know.
No,
yes,
yes,
Andrea,
maybe.
yes, please. Yes.
It's a stupid question. I'm not that familiar with it.